Deep learning refers to a subset of machine learning technique that involves training artificial neural networks with multiple layers to learn and extract high-level representation from complex data. It has been instrumental in achieving breakthroughs in computer vision, natural language processing, and autonomous driving. Deep learning algorithm handles vast amount of data and have demonstrated remarkable performance in various tasks, contributing to AI research and application advancements. Deep learning is a popular approach for building chatbots and service bots as it enables them to understand natural language inputs, recognize patterns, and generate appropriate responses. The ability of deep learning to automatically learn complex representations, its advancements in transfer learning, and its resemblance to the human brain makes it fascinating and powerful field of study that continues to transform various domains of artificial intelligence. Professionals with deep learning skills can access various career opportunities, including roles like deep learning engineer, machine learning engineer, data scientist, computer vision engineer, and natural language processing engineer. Based on the data from Glassdoor, the average annual salary for deep learning professionals in the United States is around $109,000. The average annual salary for deep learning professionals in India is 8 lakhs. Now, let's begin by understanding the basics of deep learning.
My name is Richard Kirshner with the Simplilearn team, and today we're going over the deep learning tutorial. What is deep learning? Deep learning is a type of machine learning that works on the basis of functionalities of human brain. It trains machines to work on vast volumes of structured and unstructured data. Deep learning uses the concept of neural networks that is derived from the structure of a human brain. And if you've ever seen images of a human brain network, you have dendrites, inputs. You have cell, which is a nucleus, as your nodes. You have synapses, which create weights, and an axon, which create an output. Now, this is a very simplified version of the human brain. And there are certain sets of cells that are strung together very similar to how today's neural networks perform. But they still have a long ways to go, and the human brain is still significantly more complex with hundreds of different kinds of cells and different interactions that we don't see yet. So what is deep learning? Artificial intelligence. So you have your AI is a method of building smart machines that are capable to think like human and mimic their actions. Be careful with that definition. We're a long way from a human cyborg coming in and taking over. When we talk about this, we're usually talking about automating single kind of instances or things going on. How do we automate a new process? How do we automate a small robot to do something? How do we get a drone to fly out and when it loses contact to turn around and come back in the direction it came from? Those are very simple processes and significantly lower than the scale of like what human thinking does. Now, a subcategory of artificial intelligence is machine learning. Machine learning is an application of AI that allows machines to automatically learn and improve with experience. There's a lot of tools out there to use with machine learning. And you'll see linear regression models and things like that. They're much more common when dealing with straight numbers, a linear regression model. And there's other models that just do basic math functions quite well. But then we get into one of the subcategories, deep learning. Deep learning is a subfield of machine learning that is used to extract patterns from data using neural networks. And again, we're talking about complicated patterns. When we talk about image processing and things like that, they're not as straightforward as the numbers in stock exchange. So you start looking at another way to solve these problems and figure out, is that a raccoon in the picture or something? Much more complicated.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
Deep learning performance. So when we talk about performance of deep learning and the amount of data, the performance goes up. The more data you have, the higher the performance. When we talk about a lot of machine learning platforms, they kind of peak out at a lower level. So again, you can think of this as having thousands of pictures of raccoons, like I said before, versus the numbers in a stock exchange, which are very rigid and very clear. You have a close and an open in the stock exchange kind of thing. Where when you have an image of a raccoon, the color shading, all kinds of things go into trying to figure out, is it a raccoon? So when we look at what is a neural network, and we really look into kind of a nice image of it, Today's neural networks usually have a layer of inputs, and you'll see here we have input 1, 2, and 3 with x1, x2, x3. So you have your input layer, you have your hidden layers. This might have multiple layers depending on what you're working on. Then you have your output layer, which in this case we have two outputs, y1 and y2. And you can also see the connectivity here. So everything in the first row connects with everything in the second row in the hidden layer. And if you had another hidden layer, everything in the first hidden layer would connect to the second hidden layer, and then everything in the second hidden layer would connect to each of the outputs. And then they'd make calculations based on that. And this is interesting because there's so many different aspects of neural networks nowadays that are changing this basic configuration. They find that if you skip a hidden layer or two with your input going through, that actually changes the results and works better in some cases. There's also convolutional neural networks which look at windows and adding up the numbers in them. There's a lot of complexity when we start getting into the different aspects of what you can do and how you build neural networks. And again, it's very much in an infant stage, so this basic diagram does a great job of capturing what it looks like now. The input layer is responsible to accept the inputs in various formats. The hidden layers, again there's that S, could be multiple layers, is responsible for extracting features and hidden patterns from the data. And patterns and features is important. We want to look at features. You usually talk about features as your input. You have input 1 is one feature, input 2 is another feature. If you're looking at the iris data, it might be the width and length of the petal. Each one of those would be a feature. You have these nodes which generate a number that doesn't really have a specific representation, but it becomes a way of looking at it, adding the features together and creating an importance value there. And the output layer produces the desired output after completing the entire processing of the data. What is a perceptron? A perceptron is a binary classification algorithm proposed by Frank Rosenblatt. And you'll see here we have our constants come in our inputs. We have a constant 1 for the bias. The bias is important. You can go back to Euclidean geometry where you have a line y equals mx plus b, b being the y-intercept. That's what that constant is there needs to be some kind of adjustment that basically is the y-intercept. And you have your inputs, you have your weights, you have your weighted sum, your activation function, and an output of 0 or 1. And so here we have, we'll go ahead and walk through these. We have x1, x2, x3 are the inputs. W0, W1, W2, W3 are the weights. Weights are values that determine the strength of the connection between two neurons. And if we go back to this slide, let me just flash back here to this slide, you can see how each one of these nodes has multiple inputs. So when you look at the hidden layer of the outputs, they have multiple inputs. So each one of these nodes has these inputs. They might be the original features coming in. They might be the layer of nodes before. And so you have your x1, x2, and x3 are the input into your node. Your weights are the weighted values that determine the strength of the connection between two neurons. The input neurons are multiplied with the weight, and a bias is added. There's that 1 which is weighted, the y-intercept in Euclidean geometry, to give the resulted weight sum. The activation function applies a step to check if the output of the weighting function is greater than 0 or not. There's a lot of ways to do an activation function, but this is the most common, or the most, not common, but the most easy to see way of doing an activation on here. So we look at, here we go, walking back through this diagram and taking a closer look at it. We have the predicted output is compared with the actual output. So once you go through the step and it adds everything together in there, and these are your weights are multiplied, they're just multiples. So you have feature of x1 times weight of 1 plus feature of x2 times weight of 2, so on, plus the weight times the bias. And we go ahead and compute all those all the way through. The node comes out and we have the actual output, and then we go ahead and have a predicted output. What do we think it's going to be? And this is on each node. So keep in mind we're zero in on the node. This isn't the whole process because this actually goes through all the nodes, but there's another step in here when we get to that part. The error in the network is estimated using the cost function, and backpropagation technique is used to improve the performance. So when we look at the in the back propagation algorithm, the cost function is minimalized by changing weights and biases in the network. And you can see here we have our input layer, we have our hidden layers, and we have our output layer. And so you could think of this as we have our actual output. We predict what it's going to be. In this case, we have two outputs. We might predict that it's either nothing there or a raccoon. So one of them comes up and says, I don't see any kind of animal, and the other one says, this is a raccoon. So it's either yes or no. And if it gets it wrong, it says, that's wrong, and it sends that error back. And that error goes to the first set of weights, which then go to the hidden layers and their set of weights, which goes back to B1, the other layer, and their set of weights. And it adjusts those weights as it goes backwards. And it says, hey, this is the error on the output. We kind of adjust it a little bit. The part that we don't adjust in the first set of weights, we say, there's still an error, so we send it to the second set of weights and so forth. What happens is as we adjust these weights, each one of these nodes starts creating kind of a category or something to look for in whatever image or data we have going in. And so for making a better predictions, a number of epochs are executed where the error is determined by the cost function. Now epoch is an important thing to keep track of. Epochs is if you have a large or any data set, and let's say you've split out your test date and your training data set and you're running your data through, how many times do you have to run all of that data through before you start getting something that is usable? Till the error goes down to, you can't adjust the error anymore. It's the lowest error you can get. So each time you go through a full set of data, before you repeat and go through the same data, that's called an epoch. The error is backward propagated until a sufficiently small error is achieved. And again, that's what we're talking about. We're trying to minimize the error. So we get to a point where that error really isn't changing anymore. You just have the same error coming out. And there's other ways to weight that error too. The cost function or loss function measures the accuracy of the network. The cost function tries to penalize the network when it makes errors. And you can see here we have a formula for the cost function. C equals 1/2 of the y predicted minus the y, the actual y, squared. And of course the squared value removes the sign because we don't know whether it's plus or minus when you look at an error. And then the C, this is your cost function. How much is it going to cost? How much of an error do we really have that we're sending back? And so we have, with the cost function, we can look at this, we can look at it as a loss, and the epoch, again, that's every time we go through the data, that's an epoch. How many epoch runs are we going to go? And so we have a nice graph here that shows like a very high learning rate, low learning rate. Different data is going to change depending on what you're working on. They put the yellow as a good learning rate because it has a nice slope to it, and you think, yeah, the more epochs I go in, the lower the loss. So that means you're going in a good direction there. And as you curves down, it gets to the best answer, has the lowest loss on there. So looking at types of neural networks, we have the GAN, we have the DBN, the RBFN, the autoencoder, the RNN, the LSTM. This is a flash of some of the main ones that are out there. There are now so many variations that there's variations on the variations. And so just quickly jumping into these, you can see we have a number of them here listed. And these are just like a flash of some of the more common ones, like the GAN, General Adversarial Network, where you have two different models competing against each other until they find which one can beat the other one. Kind of think of a chess game where you keep flipping who's in charge. And then we might look at the DBN, which is a deep belief network. And they're used to recognize clusters and generate image video sequences generally. And we have the RBF network, or RBFN, which is your radial basis function network, which uses a different set of activation functions to figure out which is the right weights. Autoencoder. The autoencoder is a little different than the other ones in that it looks for an error, but the error is based in finding data that groups together. So it's a way of sorting the data out without knowing the answer. That's what an autoencoder does. RNN has a couple different definitions. Most of the time you now see it as a recurrent neural network, where the output, part of the output goes back into the input. So they call it, this was recurrent. There's also another RNN which deals with learning step by step as opposed to over a set of data and weighting it as you go. And there's the LSTM, or long short-term memory recurrent neural network. It's also an RNN, which deals with how do you sort something like a sentence out where the last word depends on what the first word was, and so it slowly weights things as it goes through to figure out what's being said. Again, these are just a quick flash, and even as I was describing them, you should have been like, well, why don't you hook an autoencoder into a GAN and then run that with a DBN? Well, there are tools to go ahead and mix and match these things. So you will actually see when you start doing layers, you might have the layers of one type of neural network feed into the next neural network, and that's actually pretty common. And we talk about deep learning libraries. There's a lot of different things out there, but the big ones that they usually talk about, and most of these are dealing with larger data, is like TensorFlow, Keras. Keras and TensorFlow play nice with each other, and Keras kind of is usually integrated with TensorFlow. Caffe, Theno, PyTorch, DL4J. These are all different deep learning libraries, and there's many more out there. There's a scikit, has a deep learning library in it under Python. Scala has one that they've been building on there. So these aren't the only ones. TensorFlow is probably the most robust one at this time, but that's not to say the other ones aren't catching up and there's not all kinds of other stuff out there.
Hey there, learner. Simplilearn brings you Master's Program in Artificial Intelligence created in collaboration with IBM. To learn more about this course, you can find the course link in the description box below.
Now, going through and talking about these things is all fun, but until you get to roll up your sleeves and take a look at the code and see what's going on, it's really hard to see what we're talking about. So we're going to go ahead and do a deep learning demo on text classification. Now, to do this, there's a lot of different editors you can use for Python. Currently my favorite's always one I'm currently using, which changes from month to month or year to year depending what projects we're doing. We want to look at Anaconda Navigator, which does a nice job building your different packages and environments, and go into Jupyter Notebook. And so we'll go into Jupyter Notebook and create our setup in there to run a neural network. And so we open up our Jupyter, we'll go ahead and create a new Python 3. And let me just bring this out to the top. There we go. So now we would have our Jupyter 3, and I like to always give it a setup on here. So this is the text classification we're doing today. We'll go ahead and rename that. And we were talking about, if you remember from the beginning of the thing, I said some of one of the most robust packages out there right now is TensorFlow, along with Keras, which usually works nicely with TensorFlow. So we're going to go ahead and be working with the TensorFlow and the Keras. We want to go ahead and do a number of imports in here. This is just set up on this. A lot of this really isn't necessary for what we're going to do. There's different things we can do. So we're going to go ahead and from future, we're going to import absolute import, division, print function. These really don't do a lot other than they help us kind of display things later on. You don't really need them. You can just do some basic print on this if you want to. So I'm not going to dig too deeply into that setup. But we do want to take a look at iteration tools, because we're always iterating over things. Again, you don't really need the iteration tools because a lot of TensorFlow will do this for you. But it's a lot of times when we're building these packages, we don't think about it. We just bring in all our tools that we might need. The big ones, though, is our Pandas DB. And let me switch to a draw thing. It's always nice to kind of maybe give us arrows here. There we go. So when we're looking at, you can see here, here's our Pandas. Pandas sits on top of NumPy, our number array. Pandas is our data frame, just makes it really easy to bring in the data, view the data, and kind of work with the file. That's what these two are for. And of course our matplot library up here is for displaying it. And then we have the sklearn These are for doing metrics and pre-processing. Some of this you can actually pull off of TensorFlow. I tend to bounce back and forth between the sklearn setup. And by the way, the sklearn has its own neural network, a real simplified one compared to what TensorFlow does. But we want to go ahead and do this in TensorFlow, where we're going to be using TensorFlow Keras. And Keras is nice because it sits on top of TensorFlow, but it's easier to use. It's a little bit like you could think of TensorFlow as being the back end, which you can program in, and Keras being a higher level language, which makes it easier to do things in. And you can see here we went ahead and printed out TF version. We're using TensorFlow as the back end, and you have the TensorFlow version 2.1.0. Always important to double check your versions. You never know what's not going to work with what version of Python and so forth, so it's important to check those. This is Python 3.6. I don't know if TensorFlow is fully integrated with 3.7 or 3.8 yet. I'm sure if it isn't, it soon will be. And so we're going to go ahead and bring some data in. This is consumercomplaints.csv. And if you want a copy of this file just for your own to play with, you can put a note, send a note to Simplilearn, and they'll be happy to send you a copy of that. And then DF stands for data frame. That's very common. And we're using the pandas to go ahead and read this comma separated variable file in. And we'll go ahead and print what they call the head. If you've never worked with data frames, usually when you see head, it means the first 5 rows of that data frame. So you can see what's going on in there. And give it just a moment to read that in. There it goes. And you'll see in here that we have a date received, a product, mortgage, credit reporting, consumer loan, credit card, subproduct, other mortgage, NAN, NAN, whatever that means, whatever, it's just missing data right there. There's nothing in there. Vehicle loan and so forth. And then, of course, different columns. And this is a data frame. Data frame has rows and columns. And a lot of times when you're processing data frames, you can think of mapping, map and reduce as a terminology. We're mapping. We're either mapping each of the rows, like you might be running a process on each row, or you're running a process on each column. And then one of the most common things would be, say, to sum parts of the row together and have a total value of cost, or maybe sum the total. You might come over here, wherever, I'm sure there's a value in here. Complaint ID, they don't actually have a value. But it'd be something you would process by column. You might want to find out how many different companies are listed here. So that might be something you'd run on the column. So that gives you an idea. We have our data frame, df head on there. And if you remember, we're looking at text classification. So that makes sense that we don't have any dollar values in there. And we're going to look at just a couple of these columns. Certainly you can do this with a number of different objects on here, but we're going to take just the columns consumer complaint narrative and the product column. And in this case, when we handle null values, there's a lot of different ways to handle null values. But in this case, we're just going to go ahead and do just the not null. We only want those that are not null in the consumer complaint narrative. And let's go ahead and print that, do the df head. In Jupyter, the last line, if you just have a variable, it automatically prints it out. So you could put print and put brackets around df head and do the same thing. And you can see here we have our consumer complaint narrative. I have outdated information on my credit report, and then you have your credit reporting and so forth on each one of these. An account on my credit card was mistaken. The company refuses to provide me verification. The complaint regards to square to something. So we're going to be looking at these complaint narratives and trying to understand them. And can we write a code to optimize that? And then one of the things we always do, like up here you'll see where we already removed the null values. I would go ahead and just double check, sum up the null values. Are there any null values in our data frame? And this is just a simple way of looking at every cell. This includes consumer complaint, the product, and so forth. And you can see here we have 0 null values, so that's good. We're not going to play with the null values today. And then we can also go ahead and take a look at our end aspect we might be looking for, which is our product. We have credit reporting, consumer loan, credit reporting, debt collection, debt collection. Let's go ahead and just take a look at this and see how many counts we have. And you can see here that there is, under debt collection, 47,000 entries. Under mortgage, there's 36,000 entries. Under credit card, we have over 18,000 entries. So this is a pretty big database. And you can see it going down all the way down here with the different entries that go underneath of product. So we have, and one of the things we don't spend a lot of time on in some of these demos is what is really defining what we're looking for. Now, if you're doing a data science project, you usually start by exploring the data and then you define what you're really looking for. And so we're kind of skipping through that particular process. It does constitute a small amount of time, but as far as the importance, it's one of the most important things you can do in data science is ask the right questions. So even though you're spending 80% of the time cleaning data, building your models and everything, that 20% of asking the right questions has a higher impact. And so you really should be making sure that you understand what the questions are. That's domain knowledge. So we're talking, in this case, banking. And so in this case, it might be that as consumer complaint comes in, we can start looking at these consumer complaints and what product they're attached to and what that means. We're not going to dig too much into the domain in asking the question, what exactly are we looking for. We really want to look into the process as far as building a neural network. And so the first thing we want to do is go ahead and split our data. We need a train set and a test set. The train size, in this case, we're going to do 80% of the data is going to be for training our neural network. And then we'll go ahead and use we'll switch that over for the test size to be the 20%. Let me go ahead and run that. And you can see here train size has 159,000 entries, and then we'll test that on, we've held out roughly 40,000 of those entries for our test size. And then for this example, we're just going to split it. The first part of the data will be for training our data, and the second part will be for testing our data. So we're not really doing a random setup in here, which is okay because this is an example. A lot of times you might split this. One of the things I do with neural networks is I will split it into 3 sections, and I will test 2 as training and the third as the test. This is obviously not big data. You don't want to do this on something that might take days to process. And then I flip it, and then so I'll run it 3 times, and those 3 times will give me a nice narrative of how good my model is, and then I'll actually run the final product on all 3 sections to program it, to train it. So it gives me a good basis of what kind of error I have versus, on test models, while having a very robust model to publish. In this case, though, we're just going to go ahead and split it based on the first part goes to the train and the second part goes to the test. So one of the next things, whenever we deal with text, and this is such an important line, I want to go ahead and just highlight the tokenize. You'll see the word tokenize, tokenizer, setting it up. We're taking the words and putting them into a format the computer can understand. There is a lot of ways to tokenize words. In some cases, you call them 0, 1, 2, 3, 4. Depending on what you're doing, it might just be a 0 or 1. So when we talk about the encoder, we're usually talking about, as far as tokenize, we actually are looking at, in this particular case, we'll be looking at each word as its own feature. So when we looked up here, remember right up here, let's see, here we go, money transfer. Let me go back up just a note here. Turn that off so I can go back up. If you remember up here, we have this right here, consumer complaint narrative. So I would be a feature, have would be a feature, outdated would be a feature, information would be a feature, on feature, my feature, credit feature, report. And you think, wow, that's a lot of features. Yes. in running through bills put out by the United States that are being voted on in the government, it comes out roughly 2.4 million different words are used in those bills. That's a lot of features. And so we're going to go ahead and look at max words, tokenize, and tokenizing words. There's a lot that is happening here in the tokenized setup. And so we'll go ahead and let me just put together some of this code here. So the tokenize is an actual object in here, text tokenizer, and it has number of words equals max words. So we're going to limit it to 1,000 words. Character level equals false. Fit on text, train narrative, only fit on the training data. And so this is kind of interesting because it drops a lot of these words. Why would it drop a word? Well, on is probably used a bunch and really doesn't have any value. So that would be one of the words they'll probably drop. And it also, there's other things it can do, like it can also combine combinations of word. It might be that this company, this complaint, these might be always together. So at some point it might actually bundle some of these words as a single feature. There's a lot of things that go into that. We're not going to go into too much detail because you really have to go through the API on these to understand all the different encoding and setups you have. This is just a really fast way to do this, and it works. I like easy and I like things that work. I don't know about you, but when I'm running through and doing a lot of different models, I might start tweaking these once I have an answer. But until then, we want to go ahead and run the encoder and do something simple like this. And so using sklearn utility to convert the label strings to number index. And so here's our encoder, label encoder, encoder fit. And this is sklearn, of course, everything's fit. And then we do ytrain equals the encoder transform train product, ytest equals encoder transform test product. Now, what's going on here, now up here we did the X, where we have, let me view up here, where we were looking at, here we go. I have outdated information on my credit card report. Now we're looking at this, credit reporting, consumer loan, credit reporting. And if you remember, this is our list of those, debt collection, here's our list of them. They're not a huge number. And so we're going to encode these differently. This is just 0, 1, 2, 3, 4, and so on. Not necessarily in that order, by the way. So be a little careful on order. So we're going to convert the labels to one hot representation is our next step. And that's what this is doing. So we have our number classes npmax ytrain plus 1. Our ytrain equals utilities to categorical. So here's where we're taking our y value in the training set, and we do the same with the test set. And we go ahead and run that. So now we've created a ytrain and a ytest where we've numbered our categorical, we've created categorical data so it's easy to read the answer and translate it back. And we've encoded up here our X, and we used a tokenizer. So a little different. Encoder puts in 0, 1, 2, 3 for the different listings. An encoder or token, you can get tongue-tied on these. A tokenizer takes and creates a huge, in this case we've limited it to 1,000 words. Each word is its own token. And to really see what we're looking at, let me go ahead and we're going to inspect the elements and see what we ended up with. Let me run this. And so we have our ytrain shape. There's our 1,000. What is that 1,000? Maximum words. So we've tokenized the top 1,000 words as each as its own feature. And the same thing with the X test. So those are X train and X test. We have our ytrain shape and our ytrain test shape. And I thought the encoder, depending on how you set it, either does 0, 1, 2, 3, or in this case it actually puts it out as 18. So it did the same thing as a tokenizer as far as putting it as a 0, 1. So you have 18 choices there. And if we count these, I'm guessing there's 18 there. Now, this is the part which is, when we look at the encoders and the tokenizers, these are the tools you need to process text. The computer doesn't see the hello, on, you have to give it a 0 or 1 in each one of those. And so this is all about the text classification part. This is how we classify text, is we have to give it something that has a number representation. So once we've sorted out our data and we've converted it into something the computer can read for doing text, we want to go ahead and create our model. And when we create our model, one of the things to be aware of is this is what we call a black box model. Now, they've come a long ways in understanding how these different processes are created, and so they're starting to understand how you can put these together and go back and say why. Why does it pick this? Why does it pick that? How does it balance that? But it's black box in that it's really hard to do. It's really hard to go in there and figure out why it picks one over the other just by looking at the neural network itself. There are other machine learning tools like Decision Tree which make it much easier to see those changes in how it branches down, but they don't perform as well in many cases. And so we're going to go ahead and build a model. We'll go ahead and run this just because it builds the model, doesn't actually start fitting it yet. Let's take a look at these different pieces. So we have our model, which is going to be sequential. That's a Keras, so we imported that at the beginning from the Keras setup. This tells us what's going on, that we're going to be running this from top to bottom. And we're going to add a dense layer. So each time you see add, we look at these add, each one of these, we're adding a row. So these are all rows. And then of course our rows. You're like, what is a row? So when we talk about row, these are your layers. We have, you can see right there, input layer. We're going to add an activation to this layer, and we're going to use the ReLU activation. Then we're going to add a dropout rate. And what this does is they found that when they process a neural network, instead of processing every neuron each time you do the backpropagation to train it, you only process some of them. So only some of them are being trained. By doing that, it's able to create the differentiation between different categories. And it actually trains much better instead of trying to train them all at once. So that's what this is right here with the dropout 0.5. And then we add dense number classes. And the dense number classes is another layer. So up here we have our add and activation ReLU layer. So we have our input, our ReLU layer with a dropout of 0.5. Then we have a dense layer which uses a softmax activation. There is a lot going on with Keras and these models. You can get lost in just the activation. Here's our two activation. ReLU is one type of activation. Softmax is another. They work differently. And you can see when we were talking about earlier, we talked about the different kinds of neural networks. In Keras and TensorFlow, each of those layers can be a different neural network layer and can function differently, and you can stack them on top of each other and feed them into each other. And then the final thing, of course, is your compile. We have what we're using for loss. Remember, we want to minimize loss. So category, this is a type of way of minimizing that loss. Atom is an optimizer. You'll find there's a number of optimizer. Atom is used for larger data sets. As you get to smaller data sets, you actually use a very different optimizer in here. And we look at the accuracy. That's just when do we stop compiling this data? How far do we go until it starts building what they call a bias? It's overfitted. We want to stop at the right moment. And then finally we get to actually training our model. This is that black box. We're going to fit it to the data. We don't know what's actually going on in there, but we want to go ahead and run it. And I'm going to go ahead and start it running because it takes a moment for it to run through, and you'll see the epic feed down here as it goes through epic 1 of 5 and so forth. We'll freeze this just for a second. There we go. So let's take a look at this. We have batch size. Batch size, oops, I meant to do that in an arrow. There we go. Batch size is how many rows of data we're going to feed at a time. So you can feed larger rows. There's different reasons to feed them at different sizes. Really, a lot of times people just leave this as a default, depending, and let it choose for them. I'm not sure why they picked 32 in this case. There's probably, when they were messing with this, 32 probably was a good batch size for fitting it. The back-end math deals with differential equations and some calculus, which we won't get into. So being aware of that this batch size affects how it does that back-end differential equation in the reverse propagation, tells us that this is actually a pretty important number. If you get it too big, it's not going to fit as well, and if you get it too small, it takes way too long to process. And a lot of times there's what they call a reinforced learning neural network, where it's batch size of 1. What does that mean? Well, that means every action you take has a feedback. You program the neural network so you can guess what your next action is. That's very common, like in trying to beat video games with a automated setup in a neural network. The epoch says we're going to go through all the data in the training set 5 times. So that's what this, remember we talked about epochs? That's what the epoch is. And we can see when I let it go out here, we're on epoch 2.5. So we'll go ahead and pause this. I'm going to go ahead and pause it for a second, let it finish running. Or while we're waiting, we can actually take a look at some of this data here and see what it's actually generating for us. And so when we look at this, accuracy, loss. So we want to minimize loss. The metrics is accuracy, and you can see that we're going to want the accuracy to go up, and we want the loss to go down. And the loss is going to be what we want to minimize. And this is just some of the metrics. And it talks about like value loss, value accuracy, and how they're changing with each time we run it. And so you get to a point where it no longer gets better or worse, and at that point you really want to stop running it. You can overfit it. And overfit it means it's going to miss some of the generalities that you need when solving some of these solutions. And then I didn't talk too much about what's actually going on here. What are we doing in the domain of this particular one, which it looks like it is trying to figure out based on a consumer complaint narrative. Maybe they send in a complaint. What product is it connected to? So maybe they get the complaints before the product or something like that. I'm not sure why you do this particular setup. That would be, again, a domain knowledge in here. So what we're doing is we're using the consumer complaint narrative to predict what product they're talking about. If someone sends in an email and says, I have outdated information on my credit report, they're probably talking about a credit card reporting. If you get a random email that says, I purchased a new car on blank, the car something something, probably a loan. That's what we're trying to do, is if you get a random input from the consumer complaint narrative, you can point to the product that they're referring to without having to call them up and ask them, I guess. It might be useful, not sure. Now that we've gone through all 5 epochs, let's go ahead and evaluate the accuracy of our trained model. And so we have, we're going to go ahead and do a score for the model.evaluate, a nice Keras setup where we can do the X test and the Y test, the batch size, verbose, and then it's going to generate a score. And one of the things, let's just go ahead and print so you can see why they broke out the score. Let me just go ahead and print the score in here. Let's go ahead and run that. And so it's testing the score. It's going to take it a moment to go through all the data. And it gives us a nice score. It says the test accuracy. These can mean a lot of different things, but we have a 0.5. To be honest, without looking at the data, I would have to look and see exactly which things it missed on and how it scored on there. But it's getting about half of it. It's able to pull in half of it and say, hey, if this is the complaint, this is what it's connected to. Keep in mind when we're talking about text, that's really good. Can you imagine some of this stuff? I don't know if you've ever worked in tech support or IT or at a counter in the mall or even in taking orders someplace as a waiter or waitress or fast food or whatever. When you try to understand people, it gets pretty crazy. So even an accuracy score like this is probably pretty good for understanding some of this text. And there might be steps you could do to improve that. And so let's go ahead and go through here and look at actually using it. And we'll punch this in. It says how to generate prediction on individual examples. We have our text labels in our encoder class. And we'll just go through a prediction equals model predict NP array of X test of I. Predict label, text labels, prediction, print, test narrative, so forth. And this is just, let's go ahead and run it because reading through print statements can be very painful sometimes unless you actually see what's going on. So when the president came out with the HARP program, ... the actual label was mortgage, the predicted label was mortgage. So when this person sent this complaint in, maybe you don't know what it's connected to yet, you can guess it's probably a mortgage. I filed a dispute with Capital One Bank on ... and it says, oh, credit card. Well, it turns out it's actually debt collection, is what it predicted. So yeah, missed a little bit. A lot of times when you dispute something, it probably is debt collection. In this case, it was specific to a credit card. Okay, so we missed that one. I am disputing account number XXS with Midland, whatever. Actual test label debt collection was debt collection. I opened a Barclay card on to help rebuild my credit card, mortgage, so forth. We can go through all of these, and you can see it does a pretty good job. It gets close, or in fact, most of these it pulled in correctly, credit card reporting. And this is a lot of what we talk about with text setup. Sentiment's a really big one. There's a whole sentimental libraries out there, whether someone is positive or negative towards something. If you're pulling off Twitter feeds, you might want to look that up. You might want to look at connection towards postings in, what was it? There was running stock. I actually do some stock programming code, so I end up coming back to that a lot. Finding sentiment feeds on different stock value and different stocks out there on out of national publications really helps trying to predict what the stock's going to do. What are people going to do in buying and selling stock? Same thing with this. We can now predict their complaints and try to figure out what it is they're complaining about.
Hey there, learner. Simplilearn brings you Master's Program in Artificial Intelligence created in collaboration with IBM. To learn more about this course, you can find the course link in the description box below.
Now, that wraps up our deep learning demo on text classification and gives you a nice introduction to deep learning as opposed to shallow learning. Bad joke on my part. But you can see how a deep learning model can go in and do a lot of things that you might not be able to do using basic linear regression or many of the other machine learning models. And text classification is one of those where neural networks really shine because they can pick up things that you don't see, you can't really measure in other ways. So what is a neural network? So hi guys, I heard you want to know what a neural network is. Here we have, looks like you just went shopping at a red tag sale. My robot's back. So as a matter of fact, you have been using neural network on a daily basis. In today's world, it's just amazing how much we use our new technology. We're not even aware of it. When you ask your mobile assistant to perform a search for you, like saying your Google or Siri or whoever you use, Amazon Web. Self-driving cars, so that's the newest thing coming out. They're just now trying to make those legal in different states in the US and around the world. Even in the UK, they now have self-driving cars going up and down the street. It's pretty amazing. These are all neural network driven. Computer games use it. So a lot of computer games are driven by neural networks in the back end as part of the game system and how it adjusts to the players. And it's also used in processing the map images on your phone. So every time you do a navigation someplace and it opens it up, they now use neural networks to help you find the quickest way to get there. Neural network. A neural network is a system or hardware that is designed to operate like a human brain. In today's development, this is so important to understand because we don't have anything else to compare it to. I'm sure someday in the future, the computer will redefine, or the neural network, or the AI, artificial intelligence, will redefine what these mean. But as far as we can today's world, in today's commercial development, we have to compare it to what humans do. So we want to compare how it operates to a human brain and how it solves problems like a human does. What can a neural network do? And really, we're just going to dive in deeper to what we just covered and look at other examples. So what can a neural network do? Well, let's list out the things neural networks can do for you. Translate text. Boy, we got Google Translate, and Microsoft has their own Translate. They have some really cool, they actually have an earpiece that's supposed to start translating as you talk. What a cool technology. What a cool time to live. Identify faces. Can you imagine all the uses for facial identification? In the case of our sample, or our code that we're going to look at later, we'll be identifying dogs and cats, so not quite as detailed as understanding whose face belongs to who. I'm waiting for the Google glasses to come out so I can see who's who when I identify faces as I'm walking around, have a little name tag over them. Not out there yet, but boy, we are close. We can identify the faces, and they have all kinds of technologies to bring that information back to us. Recognize speech goes along with the translate text. So now as you're talking into your assistant, it can use that to do commands, turn lights on, all kinds of things you can do with recognizing speech. Read handwritten text. They're starting to translate all these old text documents that they've had in storage. Instead of doing it individually where somebody's going through each text by themselves in a room, you can picture like an old Raiders of the Lost Ark theme where he's in the back, archaeologist studying the text. Now it's fed into a computer. They take a picture. They even use neural networks to take a scroll that is so messed up that they can't undo the scroll, and they x-ray it, and then they use that x-ray to translate the text off of it without ever opening the scroll. I mean, just way cool stuff they're starting to do with all this. And of course, control robots. What would be a neural network without bringing in the robots? And we have our own favorite robot in the middle who goes to our red tag cell and goes shopping for us. So, these are just a few of the wonderful things that neural networks are being applied to. It's such an infant stage technology. What a wonderful time to jump in. And there are a lot of other things it goes into. I mean, we could spend just forever talking about all the different applications from business to whatever you could even imagine. They're now applying neural networks to help us understand. So now that we talked a little bit about all the cool things you can do with a neural network, let's dive in and say, how does a neural network work? So now we've come far enough to understand how neural network works. Let's go ahead and walk through this in a nice graphical representation. They usually describe a neural network as having different layers. And you'll see that we've identified a green layer, an orange layer, and a red layer. The green layer is the input. So you have your data coming in. It picks up the input signals and passes them to the next layer. The next layer does all kinds of calculations and feature extraction. It's called the hidden layer. A lot of times there's more than one hidden layer. We're only showing one in this picture, but we'll show you how it looks like in a more detail in a little bit. And then finally we have an output layer. This layer delivers the final result. So the only two things we see is the input layer and the output layer. Now let's make use of this neural network and see how it works. Wonder how traffic cameras identify vehicles' registration plate on the road to detect speeding vehicles and those breaking the law? They got me going through a red light the other day. Well, last month. That's like the horrible thing. They send you this picture of you and all your information because they pulled it up off of your license plate and your picture. I shouldn't have gone through the red light. So here we are, and we have an image of a car, and you can see the license plate on there. So let's consider the image of this vehicle and find out what's on the number plate. The picture itself is 28 by 28 pixels, and the image is fed as an input to identify the registration plate. Each neuron has a number called activation that represents the grayscale value of the corresponding pixel range. And we range it from 0 to 1. 1 for a white pixel and 0 for a black pixel. And you can see down here we have an example where one of the pixels is registered as like 0.82, meaning it's probably pretty dark. Each neuron is lit up when its activation is close to 1. So as we get closer to black on white, we can really start seeing the details in there. And you can see again the pixel shows this one up there. It's like part of the car. And so it lights up. So pixels in the form of arrays are fed to the input layer. And so we see here the pixel of a car image fed as an input. And you're going to see that the input layer, which is green, is 1 dimension, while our image is 2 dimension. Now, when we look at our setup that we're programming in Python, it has a cool feature that automatically does the work for us. If you're working with an older neural network pattern package, you then convert each one of those rows so it's all one array. So you'd have like row 1 and then just tack row 2 onto the end. You can almost feed the image directly into some of these neural networks. The key is, though, is that if you're using a 28 by 28 and you get a picture of this 30 by 30, shrink the 30 by 30 down to fit the 28 by 28. So you can't increase the number of input, in this case green dots. It's very important to remember when you work on neural networks. And let's name the inputs x1, x2, x3 respectively. So each one of those represents one of the pixels coming in. And the input layer passes it to the hidden layer. And you can see here we now have 2 hidden layers in this image, in the orange, and each one of those pixels connects to each one of those hidden layers. And the interconnections are assigned weights at random. So they get these random weights that come through. If x1 lights up, then it's going to be x1 times this weight going into the hidden layer. And we sum those weights. The weights are multiplied with the input signal, and a bias is added to all of them. So as you can see here, we have x1 comes in, and it actually goes to all the different hidden layer nodes, or in this case, whatever you want to call them, network setup, the orange dots. And so you take the value of x1, you multiply it by the weight for the next hidden layer. So x1 goes to hidden layer 1, x1 goes to hidden layer 2, x1 goes to hidden layer 1 node 2, hidden layer 1 node 3, and so on. And the bias, a lot of times they just put the bias in as like another green dot or another orange dot, and they give the bias a value 1, and then all the weights go in from the bias into the next node. So the bias can change. We always just remember that you need to have that bias in there. There's things that can be done with it. Generally, most of the packages out there control that for you, so you don't have to worry about figuring out what the bias is. But if you ever dive deep into neural networks, you got to remember there's a bias, or the answer won't come out correctly. The weighted sum of the input is fed as an input to the activation function to decide which nodes to fire and for feature extraction. As the signal flows within the hidden layers, the weighted sum of inputs is calculated and is fed to the activation function in each layer to decide which nodes to fire. So here's our feature extraction of the number plate. And you can see these are still hidden nodes in the middle. And this becomes important. We're going to take a little detour here and look at the activation function. So we're going to dive just a little bit into the math, so you can start to understand where some of the games go on when you're playing with neural networks and you're programming. So let's look at the different activation functions before we move ahead. Here's our friendly red tag shopping robot. And so one is the sigmoid function. And the sigmoid function, which is 1 over 1 plus e to the minus x, takes the x value, and you can see where it generates almost a 0 and almost a 1 with a very small area in the middle where it crosses over. And we can use that value to feed into another function. So if it's really uncertain, it might have a 0.1 or 0.2 or 0.3, but for the most part it's going to be really close to 1 and really close to, in this case, 0 to 1. The threshold function. So if you don't want to worry about the uncertainty in the middle, you just say, oh, if x is greater than or equal to 0, if not, then x is 0. So it's either 0 or 1. Really straightforward. There's no in between in the middle. And then you have the what they call the ReLU function. And you can see here where it puts out the value, but then it says, well, if it's over 1, it's going to be 1. And if it's less than 0, it's 0. So it kind of just dead ends it on those two ends, but allows all the values in the middle. And again, this, like the sigmoid function, allows that information to go to the next level. So it might be important to know if it's a 0.1 or a minus 0.1. The next hidden layer might pick that up and say, oh, this piece of information is uncertain, or this value has a very low certainty to it. And then the hyperbolic tangent function. And you can see here it's 1 minus e to the minus 2x over 1 plus e to the minus 2x. And it's very much along the same theme. A little bit different in here in that it goes between minus 1 and 1. So you'll see some of these that go 0 to 1, but this one goes minus 1 to 1. And if it's less than 0, it's, it doesn't fire. And if it's over 0, it fires. And it also still puts out a value. So you still have a value that you can get off of that, just like you can with the sigmoid function and the ReLU function. Very similar in use. And I believe originally used to be everything was done in the sigmoid function. That was the most commonly used. And now they just kind of use more the ReLU function. The reason is, one, it processes faster because you already have the value and you don't have to add another compute the 1 over 1 plus e to the minus x for each hidden node. And the data coming off works pretty good as far as putting it into the next level if you want to know just how close it is to 0. How close is it not to functioning? Is it minus 0.1, minus 0.2? Usually they're float values. So you get like minus 0.00138 or something. So, important information, but the ReLU is most commonly used these days as far as the setup we're using. But you'll also see the sigmoid function very commonly used also. Now that you know what an activation function is, let's get back to the neural network. So finally, the model would predict the outcome of applying a suitable activation function to the output layer. So we go in here, we look at this, and we have the optical character recognition, OCR, is used on the images to convert it into a text in order to identify what's written on the plate. And as it comes out, you'll see the red node, and the red node might actually represent just a letter A. So there's usually a lot of outputs when you're doing text identification. We're not going to show that on here, but you might have it even in the order. It might be what order the license plate's in. So you might have A, B, C, D, E, F, G, the alphabet plus the numbers, and then you might have the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. So it's a very large array that comes out. It's not a small amount of, we show 3 dots coming in, 8 hidden layer nodes, 2 sets of 4. We just show 1 red coming out. A lot of times this is, 28 times 28. If you did 30 times 30, that's 900 nodes. So 28 is a little bit less than that just on the input. And so you can imagine the hidden layer is just as big. Each hidden layer is just as big, if not bigger. And then the output is going to be, there's so many digits. It's a lot. It's a huge amount of input and output. But we're only showing you just, it'd be hard to show in one picture. And so it comes up, and this is what it finally gets out on the output, is it identifies a number on the plate. And in this case, we have 08-D-03858. Error in the output is back propagated through the network, and weights are adjusted to minimize the error rate. This is calculated by a cost function. When we're training our data, this is what's used. And we'll look at that in the code when we do the data training. So we have stuff we know the answer to, and then we put the information through, and it says, yes, that was correct, or no. Because remember, we randomly set all the weights to begin with. And if it's wrong, we take that error. How far off are you? Are you off by, if it was like -1, you're just a little bit off. If it's like -300 was your output, remember when we're looking at those different options? Hyperbolic or whatever, and we're looking at the REL. The REL doesn't have a limit on top or bottom. It actually just generates a number. So if it's way off, you're going to have to adjust those weights a lot. But if it's pretty close, you might adjust the weights just a little bit. And you keep adjusting the weights until they fit all the different training models you put in. So you might have 500 training models, and those weights will adjust using the back propagation. It sends the error backward. The output is compared with the original result, and multiple iterations are done to get the maximum accuracy. So not only does it look at each one, but it goes through it and just keeps cycling through the data and making small changes in the network until it gets the right answers. With every iteration, the weights at every interconnection are adjusted based on the error. We're not going to dive into that math because it is a differential equation and it gets a little complicated. But I will talk a little bit about some of the different options they have when we look at the code.
If you seek expertise in deep learning skills and aspire to be a part of cutting-edge field of building chatbots and service bots using deep learning, our PGP in AI and ML is the ideal choice. Do check out the course link in the description for more details.
So we've explored a neural network. Let's look at the different types of artificial neural networks. And this is like the biggest area growing, is how these all come together. Let's see the different types of neural network. And again, we're comparing this to human learning. So here's a human brain. I feel sorry for that poor guy. So we have a feed-forward neural network. Simplest form of they call it an ANN. A neural network. Data travels only in one direction, input to output. This is what we just looked at. So as the data comes in, all the weights are added, it goes to the hidden layer, all the weights are added, it goes to the next hidden layer, all the weights are added, and it goes to the output. The only time you use the reverse propagation is to train it. So when you actually use it, it's very fast. When you're training it, it takes a while because it has to iterate through all your training data. And you start getting into big data because you can train these with a huge amount of data. The more data you put in, the better trained they get. The applications, vision and speech recognition, actually they're pretty much everything we talked about. Almost all of them use this form of neural network at some level. Radial basis function neural network. This model classifies the data point based on its distance from a center point. What that means is that you might not have training data, so you want to group things together and you create central points, and it looks for all the things, some of these things are just like the other. If you've ever watched the Sesame Street as a kid, that dates me. So it brings things together, and this is a great way. If you don't have the right training model, you can start finding things that are connected you might not have noticed before. Applications, power restoration systems. They try to figure out what's connected, and then based on that, they can fix the problem if you have a huge power system. Cohen's self-organizing neural network. Vectors of random dimensions are input to discrete map comprised of neurons. So they basically find a way to draw, and they say dimensions, or vectors, or planes, because they actually chop the data in 1 dimension, 2 dimension, 3 dimension, 4, 5, 6. They keep adding dimensions and finding ways to separate the data and connect different data pieces together. Applications used to recognize patterns in data, like in medical analysis. The hidden layer saves its output to be used for future prediction. Recurrent neural networks. So the hidden layers remember its output from last time, and that becomes part of its new input. You might use that especially in robotics or flying a drone. You want to know what your last change was and how fast it was going to help predict what your next change you need to make is to get to where the drone wants to go. Applications, text-to-speech, conversation model. So, I talked about drones, but, just identifying on Alexa or Google Assistant or any of these, they're starting to add in, I'd like to play a song on my Pandora and I'd like it to be at volume 90%. So you now can add different things in there and it connects them together. The input features are taken in batches like a filter. This allows a network to remember an image in parts. Convolution neural network. Today's world in photo identification and taking apart photos and trying to, have you ever seen that on Google where you have 5 people together? This is the kind of thing separates all those people so then it can do a face recognition on each person. Applications used in signal and image processing. In this case, I use facial images or Google picture images as one of the options. Modular neural network. It has a collection of different neural networks working together to get the output. So, wow, we just went through all these different types of neural networks, and the final one is to put multiple neural networks together. And I mentioned that a little bit when we separated people in a larger photo, individuals in the photo, and then do the facial recognition on each person. So one network is used to separate them, and the next network is then used to figure out who they are and do the facial recognition. Applications still undergoing research. This is the cutting edge. You hear the term pipeline, and there's actual in Python code and in almost all the different neural network setups out there, they now have a pipeline feature usually. And it just means you take the data from one neural network and maybe another neural network, or you put it into the next neural network, and then you take 3 or 4 other neural networks and feed them into another one. So how we connect the neural networks is really just cutting edge, and it's so experimental. I mean, it's almost creative in its nature. There's not really a science to it because each specific domain has different things it's looking at. So if you're in the banking domain, it's going to be different than the medical domain, than the automatic car domain. And suddenly figuring out how those all fit together is just a lot of fun and really cool. So we have our types of artificial neural network. We have our feed-forward neural network. We have our radial basis function neural network. We have our Cohen self-organizing neural network, recurrent neural network, convolution neural network, and modular neural network where it brings them all together. And the colors on the brain do not match what your brain actually does, but they do bring it out that most of these were developed by understanding how humans learn. And as we understand more and more of how humans learn, we can build something in the computer industry to mimic that, to reflect that. And that's how these were developed. So, exciting part, use case, problem statement. So this is where we jump in. This is my favorite part. Let's use the system to identify between a cat and a dog. If you remember correctly, I said we're going to do some Python code, and you can see over here my hair is kind of sticking up over the computer, a cup of coffee on one side, and then a little bit of old school, a pencil and a pen on the other side. Yeah, most people now take notes. I love the stickies on the computer. That's great. That is my computer. I have sticky notes on my computer in different colors. So not too far from today's programmer. So the problem is we want to classify photos of cats and dogs using a neural network. And you can see over here we have quite a variety of dogs in the pictures and cats, and just sorting out it is a cat is pretty amazing. And why would anybody want to even know the difference between a cat and a dog? Okay, why? Well, I have a cat door. It'd be kind of fun that instead of having like a little collar with a magnet on it, which is what my cat has, the door would be able to see, oh, that's the cat. That's our cat coming in. Oh, that's the dog. We have a dog too. That's the dog I want to let in. Maybe I don't want to let this other animal in because it's a raccoon. So you can see where you could take this one step further and actually apply this. You could actually start a little startup company idea, a self-identifying door. So this use case will be implemented on Python. I am actually in Python 3.6. It's always nice to tell people the version of Python because that does affect sometimes which modules you load and everything. And we're going to start by importing the required packages. I told you we're going to do this in Keras. So we're going to import from Keras models, a sequential from the Keras layers, conversion 2D or CONV 2D, max pooling 2D, flatten, and dense. And we'll talk about what each one of these do in just a second. But before we do that, let's talk a little bit about the environment we're going to work in. And in fact, let me go ahead and open the website, Keras's website, so we can learn a little bit more about Keras. So here we are on the Keras website, and it's keras.io. That's the official website for Keras. And the first thing you'll notice is that Keras runs on top of either TensorFlow, CNTK, and I think it's pronounced Thano or Theano. What's important on here is that TensorFlow, and the same is true for all these, but TensorFlow is probably one of the most widely used currently packages out there with the Keras. And of course, tomorrow this is all going to change. It's all going to disappear and they'll have something new out there. So make sure when you're learning this code that you understand what's going on and also know the code. I mean, when you look at the code, it's not as complicated once you understand what's going on. The code itself is pretty straightforward. And the reason we like Keras, and the reason that people are jumping on it right now and it's such a big deal is if we come down here, let me just scroll down a little bit, they talk about user friendliness, modularity, easy extensibility, work with Python. Python's a big one because a lot of people in data science now use Python, although you can actually access Keras other ways. If we continue down here is layers. And this is where it gets really cool. When we're working with Keras, you just add layers on. Remember those hidden layers we were talking about? And we talked about the ReLU activation. You can see right here. Let me just up that a little bit in size. There we go. That's big. I can add in an ReLU layer, and then I can add in a softmax layer in the next instance. We didn't talk about softmax. So you can do each layer separate. Now, if I'm working in some of the other kits I use, I take that and I have one setup and then I feed the output into the next one. This one I can just add hidden layer after hidden layer with the different information in it, which makes it very powerful and very fast to spin up and try different setups and see how they work with the data you're working on. And we'll dig a little bit deeper in here. And a lot of this is very much the same, so when we get to that part I'll point that out to you also. Now, just a quick side note, I'm using Anaconda with Python in it, and I went ahead and created my own package, and I called it the Keras Python 3.6 because I'm in Python 3.6. Anaconda is cool that way. You can create different environments real easily. If you're doing a lot of different experimenting with these different packages, you probably want to create your own environment in there. And the first thing is you can see right here, there's a lot of dependencies. A lot of these you should recognize by now if you've done any of these videos. If not, kudos for you for jumping in today. Pip install numpy, scipy, the scikit-learn, pillow, and h5py are both needed for the TensorFlow and then putting the Keras on there. And then you'll see here, and pip is just a standard installer that you use with Python. And you'll see here that we did pip install TensorFlow, since we're going to do Keras on top of TensorFlow. And then pip install, and I went ahead and used the GitHub. So git plus git, and you'll see here github.com. This is one of their releases, one of the most current release on there that goes on top of TensorFlow. And you can look up these instructions pretty much anywhere. This is for doing it on Anaconda. Certainly you'd want to install these if you're doing it in Ubuntu server setup. You'd want to get, I don't think you need the h5py in Ubuntu, but you do need the rest in there because there are dependencies in there, and it's pretty straightforward. And that's actually in some of the instructions they have on their website. So you don't have to necessarily go through this. Just remember their website on there. And then when I'm under my Anaconda Navigator, which I like, you'll see where I have environments, and on the bottom I created a new environment and I called it Keras Python 36, just to separate everything. You can say I have Python 30.5 and Python 3.6. I used to have a bunch of other ones, but I kind of cleaned house recently. And of course, once I go in here, I can launch my Jupyter Notebook, making sure I'm using the right environment that I just set up. This, of course, opens up my, in this case I'm using Google Chrome, and in here I could go and just create a new document in here. And this is all in your browser when you use the Anaconda. Do you have to use Anaconda in Jupyter Notebook? No. You can use any kind of Python editor, whatever setup you're comfortable with and whatever you're doing in there. So let's go ahead and go in here and paste the code in. And we're importing a number of different settings in here. We have import sequential, that's under the models, because that's the model we're going to use as far as our neural network. And then we have layers, and we have conversion 2D, max pooling 2D, flatten, dense, and you can actually just kind of guess at what these do. We're working in a 2D photograph, and if you remember correctly, I talked about how the actual input layer is a single array. It's not in 2 dimensions, it's 1 dimension. All these do is these are tools to help flatten the image, so it takes a 2-dimensional image and then it creates its own proper setup. You don't have to worry about any of that. You don't have to do anything special with the photograph. You let the Keras do it. And we're going to run this, and you'll see right here they have some stuff that is going to be depreciated and changed, because that's what it does. Everything's being changed as we go. You don't have to worry about that too much. If you have warnings, if you run it a second time, the warning will disappear. And this has just imported these packages for us to use. Jupyter's nice about this, that you can do each thing step by step. And I'll go ahead and also zoom in there. A little Control Plus. That's one of the nice things about being in a browser environment. So here we are back. Another sip of coffee. If you're familiar with my other videos, you notice I'm always sipping coffee. I always have in my case, latte next to me, an espresso. So the next step is to go ahead and initialize, we're going to call it the CNN, or classifier neural network. And the reason we call it a classifier is because it's going to classify it between two things. It's going to be cat or dog. So when you're doing classification, you're picking specific objects. It's a true or false, yes, no, it is something or it's not. So first thing, we're going to create our classifier, and it's going to equal sequential. So their sequential setup is the classifier. That's the actual model we're using. That's the neural network. So we call it a classifier. And the next step is to add in our convolution. And let me just do let me shrink that down in size so you can see the whole line. And let's talk a little bit about what's going on here. I have my classifier and I add something. What am I adding? Well, I'm adding my first layer. This first layer we're adding in is probably the one that takes the most work to make sure you have it set correct. And the reason I say that, this is your actual input. And we're going to jump here to the part that says input shape equals 64 by 64 by 3. What does that mean? Well, that means that our picture's coming in, and there's these pictures. Remember we had like the picture of the car was 128 by 128 pixels? Well, this one is 64 by 64 pixels. And each pixel has 3 values. That's where these numbers come from. And it is so important that this matches. I mentioned a little bit that if you have like a larger picture, you have to reformat it to fit this shape. If it comes in as something larger, there's no input nodes. There's no input neural network there that will handle that extra space. So you have to reshape your data to fit in here. Now, the first layer is the most important, because after that, Keras knows what your shape is coming in here, and it knows what's coming out. And so that really sets the stage. Most important thing is that input shape matches your data coming in. And you'll get a lot of errors if it doesn't. You'll go through there and picture number 55 doesn't match it correctly. And guess what it does? It usually gives you an error. And then the activation, if you remember, we talked about the different activations on here. We're using the ReLU model. Like I said, that is the most commonly used now because, one, it's fast. It doesn't have the added calculations in it. It just says, here's the value coming out based on the weights and the value going in, and from there, you know, it's if it's over 1, then it's good, or over 0, it's good. If it's under 0, then it's considered not active. And then we have this conversion 2D. What the heck is conversion 2D? I'm not going to go into too much detail in this because this has a couple of things it's doing in here. A little bit more in depth than we're ready to cover in this tutorial. But this is used to convert from the photo, because we have 64 by 64 by 3, and we're just converting it to two-dimensional kind of setup. So it's very aware that this is a photograph and that different pieces are next to each other. And then we're going to add in a second convolutional layer. That's what the CONV stands for, 2D. So these are hidden layers. So we have our input layer and our 2 hidden layers, and they are two-dimensional because we're doing with a two-dimensional photograph. And you'll see down here that on the last one we add a max pooling 2D, and we put a pool size equals 2, And so what this is that as you get to the end of these layers, one of the things you always want to think of is what they call mapping and then reducing. Wonderful terminology from the big data. We're mapping this data through all these layers, and now we want to reduce it to only 2 sets. In this case, it's already in 2 sets because it's a 2D photograph. But we had, 2 dimensions we actually have 64 by 64 by 3. So now we're just getting it down to a 2 by 2, just the two-dimension two-dimensional instead of having the third dimension of colors. And we'll go ahead and run these. We're not really seeing anything on our run script because we're just setting up. This is all set up. And this is where you start playing, because maybe you'll add a different layer in here to do something else to see how it works and see what your output is. That's what makes Keras so nice, is I can, with just a couple flips of code, put in a whole new layer that does a whole new processing and see whether that improves my run or makes it worse. And finally, we're going to do the final setup, which is to flatten. Classifier add a flatten setup, and then we're going to also add a layer, a dense layer, and then we're going to add in another dense layer, and then we're going to build it. We're going to compile this whole thing together. So let's flip over and see what that looks like. And we've even numbered them for you. So we're going to do the flattening. And flatten is exactly what it sounds like. We've been working in a two-dimensional array of picture, which actually is in 3 dimensions because of the pixels. The pixels have a whole other dimension to it of 3 different values. And we've kind of resized those down to 2 by 2. But now we're just going to flatten it. I don't want to have multiple dimensions being worked on by Tensor and by Keras. I want just a single array, so it's flattened out. And then step 4, full connection. So we add in our final 2 layers, and you could actually do all kinds of things with this. You could actually leave out this some of these layers and play with them. You do need to flatten it. That's very important. Then we want to use the dense. Again, we're taking this and we're taking whatever came into it. So once we take all those different, the 2 dimensions or 3 dimensions as they are, and we flatten it to 1 dimension, we want to take that and we're going to pull it into units of 128. They got that. You can say, where did they get 128 from? You could actually play with that number and get all kinds of weird results. But in this case, we took the 64 plus 64 is 128. You could probably even do this with 64 or 32. Usually you want to keep it in the same multiple of whatever the data shape you're already using is in. And we're using the activation, the ReLU, just like we did before. And then we finally filter all that into a single output. And it has how many units? 1. Why? Because we want to know whether true or false. It's either a dog or a cat. You could say 1 is dog, 0 is cat. Or maybe you're a cat lover and it's 1 is cat and 0 is dog. And if you love both dogs and cats, you're going to have to choose. And then we use the sigmoid activation. If you remember from before, we had the ReLU and there's also the sigmoid. The sigmoid just makes it clear it's yes or no. We don't want any kind of in-between number coming out. And we'll go ahead and run this, and you'll see it's still all in setup. And then finally we want to go ahead and compile. And let's put the compiling our classifier neural network. And we're going to use the optimizer Atom. And I hinted at this just a little bit before. Where does Atom come in? Where does an optimizer come in? Well, the optimizer is the reverse propagation. When we're training it, it goes all the way through and says error, and then how does it readjust those weights? There are a number of them. Atom is the most commonly used, and it works best on large data. Most people stick with the Atom because when they're testing on smaller data, see if their model is going to go through and get all their errors out before they run it on larger data sets. They're going to run it on Atom anyway, so they just leave it on Atom, most commonly used. But there are some other ones out there. You should be aware of that you might try them if you're stuck in a bind, or you might explore that in the future. But usually Atom is just fine on there. And then you have 2 more settings. You have loss and metrics. We're not going to dig too much into loss or metrics. These are things you really have to explore Keras because there are so many choices. This is how it computes the error. There's so many different ways to on your back propagation and your training. So we're using the Atom model, but you can compute the error by standard deviation squared. They use binary cross entropy. I'd have to look that up to even know what that is. There's so many of these. A lot of times you just start with the ones that look correct, that are most commonly used, and then you have to go read the Keras site and actually see what these different losses and metrics and what different options they have. So we're not going to get too much into them other than to reference you over to the Keras website to explore them deeper. But we are going to go ahead and run them. And now we've set up our classifier. So we have an object classifier, and if you go back up here, you'll see that we've added in step 1, we added in our layer for the input. We added a layer that comes in there and uses the ReLU for activation, and then it pulls the data. So this is even though these are two layers, the actual neural network layer is up here, and then it uses this to pull the data into a 2x2. So into a two-dimensional array from a three-dimensional array with the colors. Then we flatten it. So there's our add or flatten. And then we add another dense, what they call dense layer. This dense layer goes in there and it downsizes it to 128. It reduces it. So you can look at this as we're mapping all this data down the two-dimensional setup, and then we flatten it. So we map it to a flattened map, and then we take it and reduce it down to 128. And we use the ReLU again. And then finally we reduce that down to just a single output, and we use the sigmoid to do that, to figure out whether it's yes, no, true, false, in this case cat or dog. And then finally, once we put all these layers together, we compile them. That's what we've done here. And we've compiled them as far as how it trains to use these settings for the training, backpropagation. So if you remember, we talked about training our setup. And when we go into this, you'll see that we have two data sets. We have one called the training set and the testing set. And that's very standard in any data processing, is you need to have, that's pretty common in any data processing, is you need to have a certain amount of data to train it, and then you got to know whether it works or not. Is it any good? And that's why you have a separate set of data for testing it, where you already know the answer, but you don't want to use that as part of the training set. So in here we jump into part 2, fitting the classifier neural network to the images. And then from Keras, and let me just zoom in there. I always love that about working with Jupyter Notebooks. You can really see. We're going to come in here. We do the cross pre-processing an image, and we import image data generator. It's so nice of Keras. It's such a high-end product right now going out. And since images are so common, they already have all this stuff to help us process the data, which is great. And so we come in here. We do train data gen, and we're going to create our object for helping us train it, for reshaping the data so that it's going to work with our setup. And we use an image data generator, and we're going to rescale it. And you'll see here we have 1 point, which tells it it's a float value on the rescale over 255. Where does 255 come from? Well, that's the scale in the colors of the pictures we're using. They're value from 0 to 255. So we want to divide it by 255, and it'll generate a number between 0 and 1. They have shear range and zoom range. Horizontal flip equals true. And this, of course, has to do with if the photos are different shapes and sizes. Like I said, it's a wonderful package. You really need to dig in deep to see all the different options you have for setting up your images. For right now, though, we're going to just stick with some basic stuff here. And let me go ahead and run this code. And again, it doesn't really do anything because we're still setting up the pre-processing. Let's take a look at this next set of code. And this one is just huge. We're creating the training set. So the training set is going to go in here, and it's going to use our train data gen we just created, .flow from directory. It's going to access, in this case, the path, data set, training set. That's a folder. So it's going to pull all the images out of that folder. Now, I'm actually running this in the folder that the data set's in. So if you're doing the same setup and you load your data in there and you're doing this, make sure wherever your Jupyter Notebook is saving things to that you create this path, or you can do the complete path if you need to, C:/, etc. And the target size, the batch size, and class mode is binary. So the classes, we're switching everything to a binary value. Batch size, what the heck is batch size? Well, that's how many pictures we're going to batch through the training each time. And the target size, 64 by 64. A little confusing, but you can see right here that this is just a general training, and you can go in there and look at all the different settings for your training set. And of course, with different data, we're doing pictures. There's all kinds of different settings depending on what you're working with. Let's go ahead and run that and see what happens. And you'll see that it found 800 images belonging to one classes. So we have 800 images in the training set. And if we're going to do this with the training set, we also have to format the pictures in the test set. Now, we're not actually doing any predictions. We're not actually programming the model yet. All we're doing is preparing the data. So we're going to prepare a training set and the test set. So any changes we make to the training set at this point also have to be made to the test set. So we've done this thing. We've done a train data generator. We've done our training set, and then we also have, remember, our test set of data. So I'm going to do the same thing with that. I'm going to create a test data gen, and we're going to do this image data generator. We're going to rescale 1 over 255. We don't need the other settings, just the single setting for the test data gen. And we're going to create our test set. We're going to do the same thing we did with the test set, except that we're pulling it from the test set folder. and we'll run that. And you'll see in our test set we found 2,000 images. That's about right. We're using 20% of the images as test and 80% to train it. And then finally we've set up all our data. We've set up all our layers, which is where all the work is cleaning up that data and making sure it's going in there correctly. And we are actually going to fit it. We're going to train our data set. And let's see what that looks like. And here we go. Let's put the information in here. And let's just take a quick look at what we're looking at with our fit generator. We have our classifier.fit generator. That's our back propagation. So the information goes through forward with a picture, and it says, oh, you're either right or you're wrong, and then the error goes backward and reprograms all those weights. So we're training our neural network. And of course we're using the training set. Remember we created the training set up here. And then we're going steps per epoch. So it's 8,000 steps. Epoch means that's how many times we go through all the pictures. So we're going to rerun each of the pictures, and we're going to go through the whole data set 25 times. But we're going to look at each picture during each epoch 8,000 times. So we're really programming the heck out of this and going back over it. And then they have validation data equals test set. So we have our training set, and then we're going to have our test set to validate it. So we're going to do this all in one shot. And we're going to look at that, and they're going to do 200 steps for each validation. And we'll see what that looks like in just a minute. Let's go ahead and run our training here. And we're going to fit our data. And as it goes, it says epoch 1 of 25. You start realizing that this is going to take a while. On my older computer, it takes about 45 minutes. I have a dual processor. We're processing 10,000 photos. That's not a small amount of photographs to process. So if you're on your laptop, which I am, it's going to take a while. So let's go ahead and go get our cup of coffee and a sip and come back and see what this looks like. So I'm back. You didn't know I was gone. That was actually a lengthy pause there. I made a couple changes, and let's discuss those changes real quick and why I made them. So the first thing I'm going to do is I'm going to go up here and insert a cell above, and let's paste the original code back in there. And you'll see that the original thing was steps per epoch 8,000, 25 epochs, and validation steps 2,000. And I changed these to 4,000 epochs, or 4,000 steps per epoch, 10 epochs, and just 10 validation steps. And this will cause problems if you're doing this as a commercial release. But for demo purposes, this should work. And if you remember, our steps per epoch, that's how many photos we're going to process. In fact, let me go ahead and get my drawing pen out. And let's just highlight that right here. Well, we have 8,000 pictures we're going through. So for each epoch, I'm going to change this to 4,000. I'm going to cut that in half. So it's going to randomly pick 4,000 pictures each time it goes through an epoch. And the epoch is how many processes. So this is 25, and I'm just going to cut that to 10. So instead of doing 25 runs through 8,000 photos each, which you can do the math of 25 times 8,000, I'm only going to do 10 through 4,000. So I'm going to run this 40,000 times through the processes. And the next thing I noted you'll want to notice is that I also changed the validation step. And this would cause some major problems in releasing because I dropped it all the way down to 10. What the validation step does is it says we have 2,000 photos in our trainings or in our testing set. And we're going to use that for validation. Well, I'm only going to use a random 10 of those to validate. So not really the best settings, but let me show you why we did that. Let's scroll down here just a little bit. And let's look at the output here and see what's going on there. So I've got my drawing tool back on, and you'll see here it lists a run. So each time it goes through an epoch, it's going to do 4,000 steps. And this is where the 4,000 comes in. So that's where we have epoch 1 of 10, 4,000 steps. So it's randomly picking half the pictures in the file and going through them. And then we're going to look at this number right here. That is for the whole epoch, and that's 2,411 seconds. And if you remember correctly, you divide that by 60, you get minutes. If you divide that by 60, you get hours. Or you can just divide the whole thing by 60 times 60, which is 3,600. If 3,600 is an hour, this is roughly 45 minutes right here. And that's 45 minutes to process half the pictures. So if I was doing all the pictures, we're talking an hour and a half per epoch times 36. Or no, 25. They had 25 up above. 25. So that's roughly a couple days. A couple days of processing. Well, for this demo, we don't want to do that. I don't want to come back the next day. Plus, my computer did a reboot in the middle of the night. So we look at this and we say, okay, we're just testing this out. My computer that I'm running this on is a dual core processor, runs 0.9 gigahertz per second. For a laptop, it was good about 4 years ago, but for running something like this, it's probably a little slow. So we cut the times down, and the last one was validation. We're only validating it on a random 10 photos. And this comes into effect because you're going to see down here where we have accuracy, value loss, value accuracy, and loss. Those are very important numbers to look at. So the 10 means I'm only validating across 10 pictures. That is where, here we have value, this is ACCs for accuracy. Value loss, we're not going to worry about that too much, and accuracy. Now accuracy is while it's running, it's putting these two numbers together. That's what accuracy is. And value accuracy is at the end of the epoch. What's our accuracy into the epoch? What is it looking at? In this tutorial, we're not going to go so deep, but these numbers are really important when you start talking about these two numbers reflect bias. That is really important. I'll just put that up there. And bias is a little bit beyond this tutorial, but the short of it is if this accuracy, which is being our validation per step, is going down, and the value accuracy continues to go up, that means there's a bias. That means I'm memorizing the photos I'm looking at. I'm not actually looking for what makes a dog, what makes a cat. I'm just memorizing them. And so the more this discrepancy grows, the bigger the bias is. And that is really the beauty of the Keras neural network. It has a lot of built-in features like this that make that really easy to track. So let's go ahead and take a look at the next set of code. So here we are into part 3. We're going to make a new prediction. And so we're going to bring in a couple tools for that, and then we have to process the image coming in and find out whether it's an actual dog or cat, if we can actually use this to identify it. And of course the final step of part 3 is to print prediction. We'll go ahead and combine these, and of course you can see me there adding more sticky notes to my computer screen, hidden behind the screen, and last one was don't forget to feed the cat and the dog. So let's go ahead and take a look at that and see what that looks like in code and put that in our Jupyter notebook. All right, and let's paste that in here. And we'll start by importing NumPy as NP. NumPy is a very common package. I pretty much import it on any Python project I'm working on. Another one I use regularly is pandas. They're just ways of organizing the data. And then NP is usually the standard in most machine learning tools as the return for the data array. Although, you can use a standard data array from Python. And we have Keras pre-processing, import image. This should all look familiar because we're going to take a test image and we're going to set that equal to, in this case, cat or dog 1, as you can see over here. And let me get my drawing tool back on. So let's take a look at this. We have our test image we're loading, and in here we have test image 1, and this one data hasn't seen this one at all, so this is all new. Oh, let me shrink the screen down. Let me start that over. So here we have my test image, and we went ahead and the Keras processing has this nice image setup. So we're going to load the image and we're going to alter it to a 64 by 64 print. So right off the bat, Keras is nice that way. It automatically sets it up for us so we don't have to redo all our images and find a way to reset those. And then we use all those to set the image to an array. So again, we're all in pre-processing the data, just like we pre-processed before with our test information and our training data. And then we use the NumPy. Here's our NumPy. That's from our right up here, import NumPy as NP. Expand the dimensions, test image, axes equals 0. So it puts it into a single array. And then finally, all that work, all that pre-processing, and all we do is we run the result. We click on here and we go result equals classifier predict test image, and then we find out, well, what is the test image? And let's just take a quick look and just see what that is. And you can see when I ran it, it comes up dog, and if we look at those images, there it is, cat or dog, image number 1. That looks like a nice floppy-eared lab, friendly with his tongue hanging out. It's either that or a very floppy-eared cat. I'm not sure which. But according to our software, it says it's a dog. And we have a second picture over here. Let's just see what happens when we run the second picture. We can go up here and change this from dog image 1 to 2. We'll run that, and it comes down here and says cat. You can see me highlighting it down there as cat. So our process works. We are able to label a dog and a cat just from the pictures. There we go, cleared my drawing tool. And the last thing I want you to notice, when we come back up here to when I ran it, you'll see it has an accuracy of 1 and the value accuracy of 1. Well, the value accuracy is the important one because the value accuracy is what it actually runs on the test data. Remember, I'm only validating it on a random 10 photos, and those 10 photos just happen to come up 1. Now, when they ran this on the server, it actually came up about 86%. This is why cutting these numbers down so far for a commercial release is bad. So you want to make sure you're a little careful of that when you're testing your stuff, that you change these numbers back when you run it on a more enterprise computer other than your old laptop that you're just practicing on or messing with. And we come down here, and again, we had the validation of cat. And so we have successfully built a neural network that could distinguish between photos of a cat and a dog. Imagine all the other things you could distinguish. Imagine all the different industries you could dive into with that, just being able to understand those two different pictures. What about mosquitoes? Could you find the mosquitoes that bite versus the mosquitoes that are friendly? It turns out the mosquitoes that bite us are only 4% of the mosquito population, if even that, maybe 2%. There's all kinds of industries that use this, and there's so many industries that are just now realizing how powerful these tools are. Just in the photos alone, there is a myriad of industries sprouting up. And I said it before, I'll say it again, what an exciting time to live in with these tools that we get to play with.
Hey there, learner. Simplilearn brings you Master's Program in Artificial Intelligence created in collaboration with IBM. To learn more about this course, you can find the course link in the description box below.
What is deep learning? Again, this video is not about deep learning, but there are other videos we have created in detail about what is deep learning. In this video, we'll just touch upon the basics, so that's like a nice segue into TensorFlow. So deep learning is in a way a subset of machine learning, and we use primarily neural networks in deep learning, and the underlying technology behind artificial intelligence is deep learning. And here we teach them how to recognize, let's say, images or voice and so on and so forth. So it is a learning mechanism, but here, unlike traditional machine learning, the data is far more complicated and far more unstructured. Like it could be primarily in the form of images or audio files or text files. And one of the core components of deep learning is neural network. And a neural network somewhat looks like this. There is something known as an input layer, and then there is an output layer, and in between there are a bunch of hidden layers. So typically there would be at least one hidden layer, and anything more than one hidden layer is known as a deep neural network. So any neural network with more than 3 layers altogether, right, is known as a deep neural network. All right. So what are the functions of the various layers? Let's take a quick look. So the input layer accepts the input. So this could be in the form of, let's say, if it is an image, it could be the pixel values of the images. So that's what the input layer does. And then it passes on to the hidden layers. And the hidden layers in turn perform certain computations. And they have what is known as a part of the training, they have these weights and biases that they keep updating till the training process is complete. And each neuron has multiple weights, and there will be one bias, and these are like variables, and we will see when we go into the TensorFlow code what we actually mean by that. And so that's what the hidden layer does. It does a bunch of computation and passes its values to the output layer, and then the output layer in turn gives the output. It could be in the form of a class. So for example, if we are doing classification, it tells us which class a particular image maybe belongs to. For example, let's say if this is a image classification application, then the input could be a bunch of images of maybe cats and dogs, and the output will be like, it will say, okay, if this is activated, this gives a 0 and this gives a 1, that means it is a cat. If this gives a 1 and this gives a 0, that means it is a dog. So that is a kind of a binary classification, and that can be extended with multiple neurons on the output side to have many more classes, for example. Or it can also be used for regression as well, not necessarily only classification. Again, since this video is not about deep learning or machine learning or neural network, we will probably not go into a lot of details, but you can check other videos where we have given a lot more details about neural networks and deep learning and so on. So in order to develop a deep learning application, how do you go about? Primarily, there are 2 or 3 components that are required in order to develop deep learning application. You need obviously a programming language. So typically Python is used, and that's what we are going to use in this particular video, but you can also use other languages like Java or C++ and so on. And there are some libraries that are readily available and primarily for doing machine learning and deep learning programming. So these are a list of libraries. These are by no means the exhaustive list, but some of the most common ones like Keras, Theano, TensorFlow, and so on and so forth. TensorFlow has nowadays become very, very popular. This is developed by Google, and it is an open source library. And Keras was there before. Now Keras has actually now become a part of TensorFlow as well. So it is one layer above TensorFlow. So in that sense, they are well integrated. So a combination of Keras and TensorFlow is pretty good. Then of course you have Torch and DL4j and so on and so forth. So there are multiple libraries, but this video is about TensorFlow, and we will be focusing on TensorFlow. What are the benefits of TensorFlow and what are its components? And towards the end, we will show you a code in Python. We've written a code in Python. By the way, TensorFlow can be used with multiple languages. It supports multiple languages, though Python is by far the most popular language. So let's take a look at what exactly is TensorFlow and why we are so excited about TensorFlow. So TensorFlow offers APIs. Now we can, earlier when these libraries, none of these libraries were there. Even then people were doing machine learning and deep learning and so on. But the coding mechanism was much more complicated. What these libraries like TensorFlow offer is they provide kind of a high level API so that we don't have to go really deep into writing all the stuff that is required, let's say to prepare a neural network and to even configure or even to program a neuron and so on, right? So these are done by the library. So all you need to do is they offer a higher level API. You need to use that API and call that API and maybe pass the data, and that would it's much easier rather than actually going down and writing everything by yourself. So TensorFlow, that way it offers APIs to write your code in Python or even C++ and so on, other languages, Java as well. It has an integration with R as well, apparently, okay? And it supports CPUs as well as GPUs. Now, deep learning applications are very compute intensive, especially the training process needs a lot of computation. It takes very long, as you can imagine, because the data size is large and there are so many iterative processes. There are so much of mathematical calculations, matrix multiplication, and so on and so forth. So for that, if you perform these activities on a normal CPU, typically it would take much longer, but GPUs are graphical processing units. You must have heard GPUs in the context of games and so on, because where the screen needs to be of high resolution and the images need to be of high resolution and so on. So GPUs, as the name suggests, graphical processing unit, were originally designed for that. But since they are very good at handling this kind of iterative calculations and so on, now they are being used or leveraged rather for doing or developing deep learning applications. And TensorFlow supports GPUs as well as CPUs. So I think that's one of the major advantages of TensorFlow as well. Now, again, what is exactly TensorFlow? It's an open source library developed by Google and open source, and primarily for deep learning development. But TensorFlow also supports traditional machine learning, by the way. So if you want to do some traditional machine learning, we can do it. However, it is probably a bit of an overhead to use TensorFlow for doing traditional machine learning, and this is really good for performing deep learning activities. And again, if you want to get into more details about what's the difference between machine learning and deep learning, there is another video about it. You can probably take a look at that video. What else? It is developed originally for large numerical computation. So originally when TensorFlow was developed, they never thought of it as keeping deep learning in mind, but ultimately it so happened that it's really very good for deep learning development, and therefore Google has open sourced it. And TensorFlow, as the name suggests, the data is in the form of what is known as tensors. These are like multi-dimensional arrays, and they are very handy in handling large amounts of data, and we will see that as well as we move forward. And then of course the execution mechanism is in the form of graphs, so that makes it much easier to execute this code in a distributed manner across a cluster of computers and also using GPUs and so on and so forth, right? So that's a quick overview about what is TensorFlow. We will see a little bit more detail, the two major components, that is basically the tensors and the graphs. Let's take a look at what they are. So what are tensors? Tensor is, as I mentioned earlier, it is like a multi-dimensional array in which the data is stored. Now when we are doing deep learning, especially the training process, you will have large amounts of data data, and the data is typically in a very complicated format, and it really helps when you are able to use this or store it in a compact way. And so tensors actually offer a very nice and compact way of storing the data, handling the data during computation. This is not really for storing on your hard disk or things like that, but in memory when you're doing the computation, tensors are really very handy in terms of keeping the data compact, because they are like multi-dimensional arrays. So the data is stored in tensors and then it is fed into the neural network, and then you get the output. Alright, so there are some terms associated with tensors. Let's get ourselves familiarized. One is the dimension and another is the rank. So what is dimension? Typically dimension is like the number of elements in a way. So for example, this is a 5x4 dimension tensor, and then you can have again multi dimensions, right? So this can be like 3x3x3. So that is the dimension. And then you have ranks. What are tensor ranks? Ranks are basically, traditionally we would have thought of as dimensions. That is actually, in this case, it is called rank. So it becomes easier when we see examples. So a tensor's rank is supposed to be 0 when there is only one element. We also call this as scalar. So just one element, and this is not really a vector, it's just an element like 200. It's also known as a scalar. So such a tensor is supposed to be having a rank of 0. Then you have, let's say, a one-dimensional array. This is a vector with a row of elements. This has rank of 1. Now if you have traditionally what we call as two-dimensional, like a matrix for example, then the rank is 2, and in this case the rank is 3. And it can have more ranks as well. As I mentioned, it is like a multi-dimensional array, so you can have rank 5, 6 and so on. Okay, so those are the terminologies in TensorFlow terms, dimensions and ranks. So this is just to make sure that we are speaking the same language, so whenever we talk about the rank of a tensor, you understand what exactly is meant by that. Now, in addition to tensors in which the data is actually stored, alright, so the data is stored in the tensors, and then once you have the data, there is a computation that needs to be done. Now the computation happens in the form of graphs. So what we typically in a TensorFlow program, what we do is, it's not like traditional programming where you just write a bunch of lines and then everything gets executed in sequence. Here we prepare graphs, various nodes, and then these are executed in the form of a session, and they use the data from these tensors. Now I know this is a slightly new concept for a lot of you, so it may be a little difficult to probably understand in the first cut, but when we look at the code, when we go into the tutorial, the code walkthrough, I think that time it will become much clearer as well. But to start with, just we need to keep in mind that we have to first prepare a graph, and when you're preparing the graph, none of the code is actually getting executed. You write the code to prepare the graph, and then you execute that graph. So that's the way, by creating a session, that's the way TensorFlow program works. So, and each of these computation is represented as what is known as a data flow graph. And we will also see that whenever you start TensorFlow, when you create an object, TensorFlow object, there will be what is known as a default graph, and then if required, I know probably in the beginning it may not be required, but in more advanced programming you can actually have multiple graphs. Instead of the default graph, you can create your own graph and have multiple graphs and use it as well. But there is always, whenever you create a TensorFlow object, there will be a default graph, and this will be very nicely illustrated in the example code that we will take to explain this. So there it becomes much clearer than in these slides. So the graph gets executed and it processes all the data that we are feeding. All the external data will be fed in the form of what is known as placeholders, and then you have variables and constants. Again, this will also become clear when we take a look at the code. And once you have the graph, then the execution can be enabled either on regular CPUs or on GPUs, and also in a distributed mode, so that the processing becomes much faster. As I mentioned, the training of the models in deep learning takes extremely long because of the large amount of data, and therefore using TensorFlow actually makes it much easier to write the code for GPUs or CPUs and then execute it in a distributed manner. So this is how the TensorFlow program looks. So there is you need to build a computational graph. That's the first step, and then you execute that graph. So the first step is to write the code for preparing the graph, and then you create what is known as a session, and then in that session you ask the session to execute this graph. So this will again become much clearer when we look at the code. As some of you may be aware, it's not that easy to set up the TensorFlow environment. There are several components, there are several possibilities. For example, you can set up on Windows, you can set up on Ubuntu. Now Ubuntu has multiple versions, which version to use, and then you have Python, which release of Python to use, whether to do a pip install, whether to do install using Anaconda, and how do you then link it up with Jupyter Notebook. These are multiple possibilities, and it takes up a lot of time to try all of these. So today what I'm going to do is show you a tried and tested method of setting up the TensorFlow environment. And this will help primarily those who are starting with TensorFlow so that they don't have to waste so much time on setting up the environment and experimenting with the installation and setting up of the environment. Now, what we are going to do is I will show you a method by which it is a tried and tested method. And of course, TensorFlow homepage has an install page and it shows you some ways to install, but again the challenge is the same. There are multiple versions, multiple methods shown there, so it's highly confusing for somebody who is new as to decide which path to take. So in today's session, what we are going to do is we will set up TensorFlow on Ubuntu, and I'm going to show you in a virtual box. But then if you are using a laptop with Ubuntu installed, you can straight away use the same method. However, we need to keep one thing in mind, that the various releases and versions of Ubuntu and Python and then TensorFlow, not all of them are compatible with each other. So these versions and releases need to be very specific. So I will tell you which is the version and releases, what combination is best suited for you to get started, and later on of course you can then experiment with other possibilities and other releases and so on once you get familiar with TensorFlow. To start with, I would also like to mention that it is a good idea to install or start with Ubuntu environment or a Linux, any other Linux also, but here we will focus on Ubuntu rather than Windows. So for those who are already, let's say, using a Windows system, the question may arise, what do we do? But there is an easy option. As you can see, I'm actually using a virtual box. So you need to install virtual box. Let me just show you. So this is the virtual box, Oracle VM virtual box, and there are tons of videos on YouTube how to install a virtual box and how to create a Ubuntu image. I think we will not spend time on that, but if you're using Windows, and my preference would be to set up a virtual box and set up your environment in Ubuntu image. So we will start by assuming that you have an Ubuntu environment, especially release 14.04 LTS. There are multiple Ubuntu versions, and again, we will not try to get the latest and the greatest versions or latest and greatest releases, but the focus here is to take the releases and versions which are working and where you will not waste time. So the setup process will be smooth if you stick to these releases. You can of course experiment later on with other versions and try out, but here we will be working with Ubuntu 14.04 LTS, and we will use Python 3.4, and we will use TensorFlow 1.5. This is a tried and tested combination, and I would also recommend that you use the same if you want a smooth start. And so let's get started with that. Let me log in to my Ubuntu system. Okay, so we have the Ubuntu system running here. Now, if you go to tensorflow.org, there is a page mentions how to install TensorFlow, and as you can see, there are multiple possibilities. You have Ubuntu, you have Windows and Mac OS and so on and so forth. And if you go to Ubuntu, for example, further you will get multiple options, whether you want CPU or GPU, and whether you want to do pip install or using a virtual native pip, virtual env, Anaconda, and so on and so forth. So all these options are very complicated, or rather they're very confusing, I would say, not complicated, depending on whether you're expert or, of course, I am talking about beginners here. But if you click on some of these options, they may look very easy. So for example, if we go back and if you select, for example, native pip, it may appear like, oh, this is just, one single or two steps and that's about it. Everything gets installed. You see here, it should be just one step install. If you say pip3 install TensorFlow and everything gets installed. Unfortunately, it doesn't work that way. So it's not as easy as, so don't get kind of fooled by the simplicity of the documentation here. Again, it's not their fault. Because of the multiple combinations of releases and so on and so forth, it is not that easy. So what we will do is, we will take a slightly roundabout method, which is using Anaconda, which has a few more steps, but you're sure that this is going to work. So that is what we are going to do, and that's what I'm going to show you. So what are the steps involved? Of course, I will not go exactly by what they have mentioned here. As I said, I will show you the steps which are again sure shot to work, whereas here again, if you follow just this document, there will be some variations which they have kind of not documented. So that's the reason I will show you the steps separately. All right, so these are the main 4 steps. You need to download and install Anaconda, and then create a virtual environment with Python. And the release, as I mentioned, is Python 3.4, and we will install TensorFlow version 1.5, and then we will install and configure Jupyter, which will be our development environment. All right, so let's get started. This is our Ubuntu, and let's get a terminal started here. And okay, yes, so all right, so we started the terminal, and then what we'll also do is we'll go to the Anaconda website, because we need to install Anaconda. We need to download and install Anaconda. So for that, you need to go to the Anaconda website. So you can just open a browser and Google, and you will find Anaconda website. So this is the site, anaconda.org. Click on this link and it will take you to the Anaconda website. You don't have to sign up or anything like that. Just look for the download Anaconda. So just click on that. It will take you to the download pages, and it automatically recognizes that you're on Ubuntu. So it will show you the links to download. All right. So as you can see, it has recognize that you're on a Linux operating system. So you can just click on this download, and it will start the download. There are 2 versions, of course, Python with Python 3.6 and 2.7. I recommend you start with Python 3.6. Now, just want to clarify that we will be actually using Python 3.4. This is just for the initial installation, but subsequently when we set up the virtual environment, you will see there is one more step there where we set up the virtual environment. There we will actually be using Python 3.4, so just that you're not confused. All right, so it has started the download. We just say no thanks for this, and it is downloading. While it is downloading, you can click on this link saying how to install Anaconda. So there are a couple of steps mentioned there that we will be using. So let me just, in the meanwhile, click on this. For some reason, the network is a little slow, so it's taking time. All right, so once the download is done, we will be using the options that are mentioned here. Now the first step, of course, is we are already doing the first step, which is downloading the installer for Linux. The second step is not mandatory, so it's an optional step. Most often you can actually skip that. And third step is what we are going to do. And since we are using, at this point, we are using Python 3.6, we should use this command. So basically, the terminal we have opened here is to use or to run this command. That's the reason I opened this terminal. However, make sure that the download is complete before you run this command. So we'll just wait for a couple of minutes and we'll come back once the download is done. Alright, so as you can see, the download is done. This is a fairly large file, so if you're on a slow internet or low internet bandwidth, then it might take quite a while. It's about 578 MB, and so this is the file. Now what you need to do is you need to go back to this installation steps, and let me minimize this, and yeah. So this is the command that you need to run. So you can just directly copy and paste this command from here. Okay, so I do copy, right mouse click. Now it will ask you a bunch of questions as documented here. So most of them you need to just say enter or yes, and that's about it, except for the last step. I will just show you what I mean. And here you need to press enter multiple times just to make sure you agree to all these agreement, the license agreement and so on and so forth. So once you do multiple enters, it will bring you to the next step. All right. So now here again, they say, do you accept the terms? You just say yes and then press enter. And here it will ask you a couple of questions, and pretty much you need to just go for the default version, press enter to confirm. You just say press enter, and this is primarily when it will pretty much start the installation process of Anaconda. This might take a little while, depending again on your internet speed, so you need to have some patience. We will also probably come back once this installation is done, or if it asks for any further questions. Alright, so here you'll get again one more question. Do you wish the installer to prepend? So you just say yes for this question and keep going. Now the last question, I think we are pretty much at the end, and that is about Microsoft VSS, I guess. Yeah, VS Code. So for this you can just say no, because we will not be using this, and that's it. You're done. So this is completion of installation of Anaconda. So it's always a good idea to exit and start a fresh terminal. Okay, so let's start again, a terminal. So we are done with the installation of Anaconda. The next step is to create a virtual environment with Python 3.4. So for that, this is the command conda create -n, and this is the name of your virtual environment. You can give any name, but for easy reference, I have given as TensorFlow, and we have to specify the Python version. As I mentioned earlier, we will be using the combination of Python 3.4 and TensorFlow 1.5. Now, this is not the latest version. Python has probably 3.6 at this point at the time of creation of this video, and even TensorFlow probably has the latest version as 1.7. But then these combinations sometimes may not work, and I found that after several trials and errors, 3.4 with 1.5 seems to be most reliable, and that's the reason I have chosen this. I would recommend you to try with this first if you're a beginner, and later on maybe you can try out the other permutations and combinations. Alright, one step I just wanted to show you is before we do the installation or creation of the virtual environment, if you want to just clarify or confirm whether Anaconda has been installed or not, you can run what is known as Anaconda Navigator. So you just say Anaconda Navigator. Okay, we need to edit this part. Hold on one second. I guess it is. Alright, so you see here, when you start Anaconda Navigator, this Anaconda Navigator will open up. That is an indication that Anaconda has been installed properly. So that's just a quick check, and you don't have to do anything. Just you can go back and close it once this comes up, and then in the meanwhile, let me just open one more terminal for the creation of the virtual environment. And yeah, so this is your Anaconda Navigator, and you can just say okay, don't show me, and you just say okay, and then you can close this. You can say file, you can do a file exit, or you can click on the close button, whichever. Alright, so we will exit from here. We have a terminal open here. We will use this for our next steps. Alright, so what we have to do now is type in this piece of code or this command. For some reason copy paste is not working, so it's a small command, so it shouldn't be that big of an issue. So we say conda and we say create. So this is the command for creating a new environment /-n, and then we give the name of the environment. So we can give any name for convenience. I'm just calling it TensorFlow, but you can actually name it anything. And then we need to specify with which version of Python. So we say pip Python, and then that is equal 3.4. Okay, so it will create an environment. This will take a little while. It'll ask you a question, just say yes, and then it will be done. So this is just a warning. You can simply ignore that. And for the question that it asks, you just say yes, and I think you should be good. Alright, so it says, do you want to proceed? You say yes, and then enter. This will again take a little time, so we will probably move forward and then come back once this is done. Alright, so the environment has been created. Now, it's always a good idea to, whenever some of these steps get over or each step gets over, you just exit the terminal and start afresh with a new terminal. For some reason, sometimes it causes problem if you continue. So I found that it is a safe practice to each time exit the terminal and start afresh. Now that we have an environment created, we can, by the name TensorFlow, you can enter that environment by calling the command source activate TensorFlow, or the name, whatever name you have given. So you'll see here, once you do that, you will get this, the name of the environment will be shown here. So it is like your own, again, a special environment within the system. And from here onwards, you can do other stuff like actually installing TensorFlow and so on. And you will see that it has installed Python 3 here, so 3.4, right? So it is installed. That's what we, during creation of this environment, we wanted Python 3.4, so that is what it is showing. But we are not yet done, so we need to still install TensorFlow. So in this environment, you need to run a command which will actually install the correct combination of TensorFlow. Now this is, as you can see, it's a slightly complicated command, pip install -- ignore install. So what we can do is from within here, we can go and go to TensorFlow install page, and there is a sample code there. You can pick up from there so that you don't have to type in so much. So we say TensorFlow, TensorFlow.org. And I'll also open up probably a notepad here so that we can construct that command and go here. We say Ubuntu. If you come further down, there will be, by the way, we are doing CPU installation. I think that is clear. We are not, there is a possibility to do GPU as well. We will probably create a separate video for that. And if we go here, yeah, so again, you probably, if you follow the entire document out here, it may still not work. So I do not recommend that for now, at least for beginners. But just to copy this command, because this is a fairly complicated command, so this is much easier to copy it from here. That's the reason I'm on this page, and we will then modify it according to yes. Okay, let's say copy, And don't do it directly here because that is probably not yet the right command. Let us go and create a notepad page, empty document. I'll just say tf.txt. Okay, this is just a temporary file. What we need to do here is we need to adjust this command to suit the versions that we are installing here. So let me just explain what it is, what you need to do. So first thing, you can get rid of this one. Yes, okay. Now here, these parts you can simply ignore. Here you need to go and change it to version 1.5, and I think we are good with that. Okay, so the CP34 indicates your Python 3.4. So later on, when you're trying to experiment and if you want to do other combinations of TensorFlow and Python version, then you can change this. For example, you can change this to 3.6. Both these places you need to change this to 3.6 if you're using with Python 3.6. And similarly, if you want the latest version, which is of TensorFlow, which is 1.7, you need to change this to 1.7 and so on. But at this point, to start with, if you're a beginner, I would recommend that you stick to this TensorFlow 1.5 with Python 3.4. This is tried and tested and it works. Okay. Just a word of caution that just by changing these versions, the whole thing will not work. There may be other places where you may have to, some of the steps may change. So just a word of caution that just by changing this, if you want to try out with a different version, some of the steps may also change. So you don't think that just by changing this, just one particular command, you will be fine. Okay. So that's been my experience. So to start with, I would recommend use this particular combination. All right. So it looks good. TensorFlow 1.5, and let me just reconfirm with my notes, and I think it looks good. So this is install, ignore, 1.5, CP34, and so on. Okay. Okay, so let's hit enter. So it started the process. Again, this might take a little while, so we will pause the recording and then get back when the installation is done. Okay, so looks like this installation is done, and as always, let us exit and then come back. Now you're currently in the environment, virtual environment, and it's a good practice before you exit out of the terminal to come out of the virtual environment. So just like you did source activate, you need to do source deactivate and the name TensorFlow. Okay, you will come back to the original command prompt, and then from here you can do an exit. Now we need to validate whether the TensorFlow installation has gone through properly or not. So the way to validate is to first start Python and then import TensorFlow library, see if it imports without error. So that's the best way to validate. So we'll open a terminal, and whenever you want to get into the environment, this is how you have to do. Come to environment and then say source, and obviously you can also use existing. So source activate TensorFlow. Okay, so we do this, and you need to run Python from here. And remember, you should say Python 3 because you have installed Python 3.4. Now here, when you say import TensorFlow as TF, when you get back a prompt like this without any errors, that means TensorFlow installation has been successful. If TensorFlow was not installed properly, you will get an error saying TensorFlow is not available or module doesn't exist or something like that. So TensorFlow installation is done, but now we will go through the process of installing Jupyter Notebook so that you can do your development. So let me just exit, and in order to install your Jupyter Notebook, which is going to be your development environment, we will first install IPython using conda. So conda install IPython and then pip install Jupyter. So let's first do the IPython. Conda install IPython. Again, it will ask you a question saying these are the components. Do you want to install? You just say yes. Alright, you say yes. And then once again, it will take a little while, so we might pause the recording and come back once it is done. Great, so that did not take much time anyways, so we will, as usual, we will exit, which is source deactivate, TensorFlow, exit, and then we will start a fresh terminal in order to install Jupyter. Now, in some places, they may say install Jupyter using pip3, but in my experience, it did not work with pip3, and that's the reason we will use pip. However, just keep in mind, you need to first go to the environment. So source activate TensorFlow, and you need to use this command, which is pip install Jupyter. Usually when you're on Python 3, you use pip3, but as I said, it did not work. So in my experience, it works with pip install and not pip3. So pip install Jupyter. I hope you already noticed that it is JUPYPER and not JUPI. So again, it's probably taking a little while. We will pause the recording and come back once it is done. Okay, so Jupyter installation is also done. Once again, you need to, it's a good idea, not you need to, but it's a good idea to come out of this terminal session and then start afresh. So we exit and we have a fresh terminal already available here, and we will once again go to TensorFlow and we say Jupyter Notebook. That's how you start your Jupyter Notebook. So this looks good. Now, only thing is, since we are running for the first time, what you need to do is, if you come back to your command prompt, it will show you that if you are running it for the first time, it will say that you need to copy paste this link. So you can just, for the first time, only once, you need to do this, copy this and paste it in your browser. And remember, this is only the first time when you're running Jupyter. You need to do this. Subsequently, you don't have to. It will automatically open up. Alright, so now that we have Jupyter installed and it starts up, we need to test whether TensorFlow is working fine or not. And in order to do that, you can create a new notebook and you say import TensorFlow as TF and shift enter. If everything is fine, TensorFlow is installed properly, you don't get any errors, and then it works fine. This is an indication that TensorFlow got installed successfully, and that's about it. So that's all about installing TensorFlow with Python 3.4. So remember, this is installation of TensorFlow 1.5 with Python 3.4 on Ubuntu. And once again, in case you have a Windows system, in fact, I have also done it on a Windows system, you can use VirtualBox to create a virtual environment, Ubuntu environment, and then follow these steps. And there are tons of videos to create VirtualBox, and that's the reason we have not included those steps in this. And if there are any comments, there are better ways to do this, please mention it in the comment section below, or if you need any further help, just mention it, and with your email we will respond to you.
Hey there learner, Simplilearn brings you Master's Program in Artificial Intelligence created in collaboration with IBM. To learn more about this course, you can find the course link in the description box below.
Now, what are the various elements of a TensorFlow program? As I mentioned, TensorFlow program is slightly different from regular programming that we do. So even if you're familiar with Python, this may still be new for you. The way you write a TensorFlow program is different from the regular Python programming that you would have done, or even machine learning program. You would have written some machine learning program using scikit-learn or regular Python libraries. This is different from even that. So let us see what are the various elements. So first of all, the way we handle handle data inside of a program itself is a little different from how we normally do. In a normal programming language, a variable is a variable in your program, right? So you have anything that can keep changing, you just create as a variable, or even constants in fact are actually created as variables. But in TensorFlow, the storage in the program consists of three types. One is constants, another is variable, and the third is a placeholder. So and there is a lot of difference between these types, and we will see how they vary and how they are used and so on. So constants are like variables which cannot be changed. So for example, if you define a constant like this is how you define a constant, by the way. The simplest format is like this, like for example, b is equal to tf.constant, and then you give a value here. A slightly more advanced version is you also specify the type. So you say tf.constant 2.0 tf float 32. So the type is of type float. Now, in case of constants, you cannot, during the computation, you cannot really change these values. So for example, if you want to change the value of b from 3 to 5 or any other number, it is not possible. So that is the meaning of constant. Alright, so then we have variables. So variables we are all familiar with. What are variables? Whenever we use programming, we use variables. So this is pretty much the same. This is the way you define variables, tf.variable. Now, one thing you need to note is this is the only type in which we have v capital. Okay, constant has c, small c, and placeholder as small p, but variable has capital V. And tf.variable, and then you give a value, and then you can specify what is the type, and then you can use the variable, change the variable at any point in time with a different value and so on. You can update the variable and so on. So we will see all of this in the code. I will illustrate how a variable is defined and how it can be changed, whereas a constant cannot be changed, and so on and so forth. And then we have placeholders. Placeholders are really a special type, and this may be something completely new for many of us who have been doing programming, but in TensorFlow this is a completely new concept. So this is very important to understand this. Placeholders are like variables, but only thing is that they are used for feeding the data from outside. So typically when you are performing some computations, you need to load data from a file or from an image file or from a CSV file or whatever. So there is a provision with this special kind of variables which can be fed in a regular basis, because one of the reasons for having this kind of provision is that if you get the entire input in one shot, typically it may be very difficult to handle the memory and so on. So I think that was the reason they came up with this mechanism where you can feed in batches. And there is a certain way of populating the placeholder. We call this feed_dict, feed_dict, and this is a parameter name, by the way. And you feed the placeholders, right? That is the meaning here. So there is a certain way of feeding the placeholders, and we will again see this in the example code as we move forward. Okay, so there are three types. One is the constant, which cannot be changed once you assign a value. Then you have variables, which are like normal variables we are all familiar with. And then you have placeholders. This is primarily for feeding data usually from outside, but of course you can also, for temporary testing purpose, you can feed within the program as well. But primarily the purpose of a placeholder is to get data from outside. So alright, so those were the constants, variables, and placeholders. That is how you handle data within a TensorFlow program. And then you create a graph, and once you create a graph, then you have what is known as a session, and then you create a session object, and you create a session, and then you run a particular computation or a node or an operation. And so typically what you need to do is every variable or a computation that you perform is like an operation or a node within a graph. So initially the graph will be what is known as the default graph. The moment you create a TensorFlow object or TF, this TF here you see, this is the TensorFlow object. And again in the code, when we go into the code, it will become much easier to understand. So when you create a TensorFlow object, there is like a default graph which doesn't have any operations, no nodes or anything like that. So it's like a clean slate. The moment you assign variables or constants or placeholders, each of them is, in TensorFlow terms, it is known as an operation. Again, you need to get familiar with these terms, and they are not very intuitive. This is not really an operation. You're just creating a constant or a variable, and this C is equal to A into B would traditionally or would intuitively be an operation. Here you're actually performing an operation. But in TensorFlow terms, each of these, everything is an operation. So if you're creating a constant, that is an operation. Another constant or variable, that's an operation. So you can actually run each of these, and they're also known as referred to as nodes. And when you're in your session, you will actually run each of these. You can potentially run each of these nodes. Okay, so a typical example would look like this. So you have two constants created. A is equal to tf.constant, its value is 5, b is equal to this, and then you say c is equal to a into b, and then you create a session. Now remember, all this you're just creating a graph. At this point, no execution has happened. All right, so only at this point, once you create a session and then you say session or ses.run, C is when actually this whole thing will get executed. All right, so that is a different way of programming compared to our traditional way of writing programs. So you need to get used to this new format. And when we look at the code as we move forward, and when we look in the Jupyter notebook, it'll become much easier probably to understand this rather than in the slides. So these are the slides showing the code. But what we can do is go straight into the lab and take a look at the various examples that are there, and starting from the very basic one, how you create variables. And so these are some of the slides that are showing. So this is about how to create variables, how to create constants, and the variables or constants can also be strings. So this is like our first hello world program, and we will talk about placeholders, how to define a placeholder and how to execute and populate the placeholder values into placeholder. We will see these examples in the lab. Actually, I will run the code, and we will also perform a small computation of adding and multiplying these variables, and we will, in the end, we will take up a use case implementation using TensorFlow. So let's first go and see those examples and then come back and I'll explain this use case, and then we will execute the use case in the lab.
If you seek expertise in deep learning skills and aspire to be a part of cutting-edge field of building chatbots and service bots using deep learning, our PGP in AI and ML is the ideal choice. Do check out the course link in the description for more details.
So let's go and check our lab. Okay, so I'm in the Jupyter Notebook environment, and this is one of the development environments we can use. This is regular Python. Anytime you do Python programming, we use Jupyter Notebook, or there are other ways of using other tools like PyCharm and so on. But for this particular tutorial, I'm comfortable using Jupyter Notebook, so I will show you in Jupyter Notebook. So this is the very basic example to demonstrate how to create variables and constants and placeholders, and what is the difference between them, how they behave, and so on. And as I mentioned, the assumption here is that you know at least some basic Python programming or some programming language, so at least you understand the code here. And first two pieces of code, you will not need machine learning background, but when we do the use case or the case study, there it is expected that you know at least some basic machine learning concepts. So in case you need to brush up the machine learning part, you may have to do that before you go to the third one. But here, just at least some idea of programming will be sufficient. So what are we doing here in this particular line or in this particular cell? We are importing TensorFlow. It is, as I mentioned, it is a library. So we are importing TensorFlow and we are calling it TF. So this is just a name. You can give it any name, but it is very common, and everywhere wherever TensorFlow programming is done, it is always named as TF, but you can name anything actually. Okay, so this will import the TensorFlow into my session. Now this is the way to create a variable. So let's start by creating a variable, and this is the name of my variable. I'm starting by giving a name called 0, and I say 0 is equal to tf dot variable, and then I'm giving the value of the variable here. So this is the very basic way and the simplest way to create a variable. We will see a little later there are other formats as well, but the bare minimum way of creating a variable is this. So I'm creating a variable by the name 0, and as I mentioned, you need to pay attention to the capital V here. In case of variable, it is a capital V, uppercase. Constant and placeholders are lowercase. Now I'm creating a constant, and the constant I'm naming it as 1, and the way to create a constant is tf dot constant, and then you give the value of the constant. So the value of the variable here is 0 and the value of constant here is 1. And again, constant you can also have additional parameters like a name and so on. Probably you must have seen in other tutorials or in other places where the code is written. But the basic format to construct to create a constant is this. This is sufficient to create a constant. So I created one variable and one constant. Now, what else can we do? Again, here there is no real execution happening. We are just building a graph. We have not yet executed any TensorFlow code. We are building a graph. And I will show you how the graph looks as well. First, let us understand the constants and variables and so on, and then I will show you how the graph is generated and so on. So what I want to do here is I want to add 0 and 1 and put it into a new variable called new value. So what I do here, TensorFlow offers these methods like add, assign, multiply, or you have matrix multiplication, matmul, and so on, right? So I will use one of those methods, which is tf.add, and then pass these two as parameters. So we can add a variable and a constant. There are no restrictions on that. So this is a variable and this is a constant. So if I do this, it will be okay. I did not execute this code, so it is giving an error. Now we are good. Okay. So what it has done is new value will be equal to tf.add 0, 1. So then we have one variable and one constant. Now let's say I want to change the value of the variable, because that is possible, right? So we want to change the value of the variable to something, some new value. So we have, in this case, new value has 1 because we added a 0 and a 1. So new value has 1. Now I want to assign this to this originally what we called as 0. So I will call that as update is equal to tf.assign. So assign is basically changing the value. So that's what we are going to do here. Now it has not complained. We'll just say fine, right? There are no issues. Now let us try this something similar with this 1 as well. So 0 is a variable. So we were able to change the value, and we will in a little while we will see what exactly those values are. But before doing that, now let's say I will uncomment this part and I want to do something similar for my constant, right? 1 is a constant. Now I want to, let's say, change the value of the constant and make that also something different. Okay. So if I execute this piece of code, it will give an error. Now again, the error message may not be very intuitive. This doesn't say that you cannot do this for a constant. It will just say tensor object has no attribute assign. Now that sometimes may be confusing, especially when you're starting. But the meaning here is that 1 is a constant and you're trying to modify the constant, so it will not allow. That's the reason it is complaining. So let's put that back in the comment, and okay, so that is done. So only variables you can modify. Now what do you have to do? Let's skip this piece of code. I'll come back to this in a bit. But let's say we start by creating, you remember I told you we need to create a session. So the way to create a session, there are a couple of ways of creating a session, but this is for beginners. This is the easiest way. All you need to do is assign a variable called ses, or you can give any name, and that is equal to tf.session. That is the session method here, and you create a session object by the name ses. Now what I'll do is I'll skip this as well. There is a purpose behind that. Now let's go ahead and run this piece of particular operation. Remember I mentioned that everything you need to run. So as of now the code has not really got executed. TensorFlow code has not got executed. You only created the graph. So only when you run through the session is when actually the program gets executed. So when you do this, now you see, observe that it is giving an error. Okay, the reason behind that is, remember we skipped these 2 lines of code for variables. Okay, this and then this. Now this is something very, very important to observe. If you have variables in your code, what I mean by that is, let's say you are not using variables but you have only constants and placeholders, then this will not complain and you will not get this error. But in our case, we also have variables. So whenever you have variables, in that case, you need to do an initialization. And this is just a standard code. There is nothing that we need to add or modify or anything like that. This is a standard piece of code. You create this name, of course, can be anything. You can give us any name. But this global variables initializer is what you need to call tf.global variables initializer. This will kind of initialize all the variables that you may be using. And then again, remember, this doesn't execute anything, right? So all you're doing here is you're creating an operation. But in order to run that operation, you need to also run this known as run init_op. So this operation you need to run after creating the session. All right. So we executed this. Now let us execute this. And now when I run this piece of code, it will run successfully. Okay. I hope you observed that. So it is whenever you use variables, these two lines of code. One is the operation. You need to create an operation for saying global variables initializer. And then you need to run, before running anything else, you need to do a session.run this operation. Okay. Again, only if you're using variables. Of course, you invariably in all your programs, you will use variables. You cannot just write a program with constants and placeholders. So you can pretty much assume that this has to be there in pretty much all the programs. Now again, why this has not been taken care of in the library, that's a different question, but you need to keep in mind. And always remember, if you don't do this for whatever reason, if you've forgotten, you will get an error and the error won't be intuitive. So you need to remember this, that this could be because of the variables. Okay, good. So we have seen how to create a constant, and we have seen how to create a variable, and we have seen that you cannot modify or update a constant, and we have also seen if you have variables that you need to execute or have these two lines of code to initialize the variables. And then we have seen that after creating a graph, how to run the graph in a session. And I will show you a little bit more in detail how exactly the graph gets created and how it gets executed. But this was the first very quick code on creating variables and constants. Now we will keep going, and we will also show you, or I will show you the placeholders. But before that, one more small piece of code. So this is how you write a for loop. Okay, so we are saying 5 times you run this piece of code. Now, like any Python program, this is nothing different. So you have a for loop, and this is indented. That's the reason. And therefore you say session.run update. So this will run 5 times and it will get printed. That's all. So update will run for 5 times. Each time it will come and do this particular operation. That's all we are asking the system to do. So let me just run that and show you. So it will, okay. So it has done 5 times. That's 4. It is basically adding, if you recall, it starts from 0, it adds 1 to 0, then 1 to 1, 1 to 2, and so on. So it's nothing but it is generating 5 numbers, 1, 2, 3, 4, 5. That's it. Okay. So then you can also have your constants as strings, for example. So you can also work in a similar way. You can work with strings. So most of the computation happens mainly on numerical values. So we normally handle numbers, but there will be situations where you may have to handle strings as well, or text as well. So this is an example of text operations. So you can, similar to numbers, you just create strings or store in constants. Instead of a number, you say hello is equal to tf.constant, and then you assign the string that you want it to be assigned. And then the next one is one more string, which is for world, and then you say add these two. So it is nothing but concatenation of these two words, hello and world. So we will do that. And remember, this is only creation of the graph, right? So in order to actually execute this graph, you need to run the session. Now you need to keep in mind, we don't have to create the session once again, because once you create a session, till you close the session, it remains valid. Okay. So we have created this session here. Now till you say ses.close, it will remain for you. So that's why we did not create one more. So we are just reusing that session, ses.run hello world. So in this hello world, what is the operation that we are doing here? The operation is add these two, concatenate these two. So if I run this, it will print hello world. Okay. Now that's string operation. Now we will take a look at placeholders. So this is slightly more complicated and something new even for people who have been writing programs. So, but I'll just explain it with a quick example. First of all, how do you declare or create a placeholder? You just do tf.placeholder, and the p is lowercase. Only in case of variables, the v is uppercase, but otherwise constant and placeholders, it is lowercase. And you just say, because as I mentioned, this is a placeholder that doesn't have any value. So you, unlike a constant or your variable, you will not specify any value. You just say what type of placeholder you want. And very often, most of the cases, it is a floating point. So we just say placeholder of type float32. So this tf.float32 tells the system that it is a floating point. Okay, and then so let me just run this, and then you can do some or define some computation, like for example b is equal to a into 2. Now remember, here right now a has no value, but what we are saying here is at any point later on when a gets some value, then b should be equal to twice the value of a. That's all we are saying here. Okay, and also as I mentioned earlier, we are not yet executing anything, we are just creating the graph here. Okay, so now you have that. Now how do you feed the value or populate the placeholder? There is a certain syntax in which you can populate the placeholder, and you do that using what is known as a dictionary. You're all probably familiar, those with Python especially must be familiar with the dictionaries. So you need to create a dictionary and then pass that in order to feed the placeholder. So in this particular example, if I want to run something, if I want to calculate or compute b, obviously I need to feed the value of a. So the value of a I'm feeding using this dictionary, and I'm saying that a is equal to 3. Now there are multiple ways of populating the value of a, because typically this won't be just a scalar value like in this case, right? Remember scalar, so it's just one value, one number. Typically it would be a vector or a tensor. Very often it is a tensor. So we will see step by step. So we can start with the very basic example where a can be a scalar. So in this case a is equal to 3. That's what we are saying. Feed underscore dict. In this case, feed underscore dict is the name of a variable, by the way. So you can't give anything else here. So if you just say feed is equal to this, it will give you an error. Alright, so keep that in mind. Either you specify feed underscore dict is equal to and give the dictionary, pass the dictionary, or you straight away, like in this case, this is another format. So let's see. First, let me execute this. It has given 6. Okay, I think let me see if I can clear out this particular cell so it becomes easier to understand. Okay, so it is giving you 6. Let me do that once again. Clear out this and then okay, and let me change the format. So this is one way of doing it. Another way is you don't even have to specify the name of this parameter feed underscore dict. You just pass the dictionary and it will execute. Okay, but typically this makes the code readable. So that's the reason most of the places whenever you find TensorFlow code, you will see that they explicitly mention feed underscore dict so that the code is readable. Otherwise it can get confusing. So I will also comment this and retain the other format. Okay, so I hope it's clear. So what we are doing here, we are running the operation b, and what exactly is b? B is twice a into 2. So therefore what we are doing, and therefore b gets a value of 6, and that's what is being fed into result, and that's what is getting printed here. Okay, now as I mentioned, a need not be just a scalar value. It can be a vector with a multi-dimension array and so on and so forth. So let's start showing you examples of that. Again, let me just clear out the outputs. Let me clear this, and let me also clear this for now. Okay, you can also do, before running this, we could also do clear all output. All output clear, it will clear everything, but we'll have to start all over again. So I'm just doing individually. All right. So in this example, we are taking a one-dimension array where rank is equal to 1, and I'm feeding 3, 4, 5. Now let us see what happens if I run this, right? As you can imagine, it gets multiplied. Each number gets multiplied. So the result is 6, 8, 10. Okay. Now, as I said, it can get more complicated. Now let's say this is a multi-dimensional vector. So what happens if you feed this? Okay, so as you can see, this is pretty complicated. Now, but if you feed this again, all you're doing is there is a slight change here. Again, you can also create your dictionary outside and feed that here. You don't have to directly do it here, like in this case. You see, there are variations of the exact syntax in the way you write it, right? So there is a slight variation. So in this case, you are creating the dictionary straight away here, kind of inline, but here you created the dictionary separately because it's more complicated, and then you are passing that dictionary here. So I said dictionary is equal to A, and then I'm saying this is what should be the value of A. And I'm feeding that, and then I'm using directly that dictionary here. Okay, so this is equivalent to putting this code here, right? So if we execute this, what happens? Same. So you get, because A was let's say this is a 3 by 4 by 2, right? So that is 3 by 4 by 2, right? So you see here, this is a multi-dimensional array. So you feed that, and the values you see here, it is 1, 2, 3, it became 2, 4, 6. 4, 5, 6 became 8, 10, 12. 7, 8, 9 became 14, 16, 18, and so on and so forth. Okay, I hope now you got an idea about placeholders. And in real life, what happens is you typically won't create these dictionaries manually. Since this is a quick demo, we did this. You will actually read the data into this dictionary, and then you feed that when you're doing the computation. Okay, so it could be a CSV file, or it could be an image file. So input is basically read and fed in. Usually it is also done in batches, so you don't read the entire thing because there can be a large amount of data. So that is the idea behind having these placeholders, and the way we feed these placeholders, there is a provision, deliberately there has been made a provision for this kind of getting data into the program in chunks. Okay, now in this particular example, we will close the session here, and then I will show you what is the other way of creating a session, right? So now if I close the session here, now if I try to do anything with the session, it will give us an error. So I will probably not do that right now. Now there is another way or another format, and this is a very common way of using the session, but I didn't want to start off with this because this could get a little confusing. A simpler way was to create session saying ses is equal to tf.session, but typically you will do it in what is known as a with block. This is a very common way of creating session. So once you have the graph, you would execute the graph in a session using a with block, and this is the syntax. So you say with tf.session as ses, all right, and then you put all your code here. So what will happen is you don't have to explicitly close the session. The moment this with block gets completed, the session gets closed. Okay, so let's just take a quick look at this example. Now, if we let me clear this current output, we clear. Okay, so this is the hello world example. A little bit earlier we did that. So I'm doing with tf.session as session result is equal to ses.run hello plus world, and then I say print result. Okay, so within this with block, I'm doing all my computation, and this gets executed. Now let's say I try to run. Remember, I created a session here. Now if I want to, let's say, do something like run ses.run a, it is giving an error because the session is no longer valid, right? So you cannot, either you have to run this. If you want to run this, you have to run this in this with block, or you shouldn't have closed the session here, right? You remember this, we said session.close. So since we have closed the session, there is no active session, therefore it is giving an error. Okay, now there is a third way of creating a session, but for now I will skip it because that is very, very specific to notebooks and so on, so we will just avoid it. You start with, for beginners, I think the best way is to start with creating a separate session and then writing your code and then closing your session. Now of course, remember, if you don't do this part, ses.close, it will not give any error or anything like that. Only thing is that it's a good practice and your resources will get released. Otherwise, if you do multiple of these programs, if they are running, then your resources will get blocked. That's the only thing. And to start with, it is simpler to do it this way. So initially when you're doing, you start with this. But as you move forward, as you become familiar with TensorFlow programming, I would recommend all of you to get into this model. Most of the programming, TensorFlow programming, is done like this with tf.session as says. Okay. All right. So that was one book or one page of code that we have done explaining about variables, constants, and placeholders. Now let me explain how the graph works. So in this example, we are going to see how the graph is created, how the graph gets executed, and so on. Okay, now that we got a understanding of constants and variables and placeholders. Okay, so we will start as usual by importing our library. And as I said, whenever you create a TF or TensorFlow object, there will be what is known as a default graph. And you can get a handle of that by saying get default graph. So let's do that, and you can display the operations. Remember, every node in the graph is considered as an operation, right? So as of now, as you can see, we have not done anything. We have not created a constant or variable or nothing, right? So there is no operation. So by the way, let's do one thing. Let's start with all output clear so that I don't have to again do individually. So I'll just run these 2 lines of code. Okay. Now, so we have the default graph, and as of now there are no operations. So there is a method called get_operations which will kind of display or show what are the various operations that have been performed on the graph. So as I said, to start with, there have no operations been performed. So when I try to display, it's empty. There are nothing is there, no operations. Okay. Now let's see what happens when we slowly, step by step, start writing or building the graph. So my first step may be to create a constant. Okay. Remember, in the previous example, I have shown you how to create a constant in the most simple or the simplest way, which is like constant and then the number, right? Now, a small extension of that is you can actually give a name to your constant. Now again, this need not be the same. I can say a is equal to name and xyz. I can give anything here. Okay, this is just for your reference, but here for simplicity, because there is a purpose why I'm using the same name as the name of the variable, and there are other reasons as well why you would give a name again to a constant or a variable. This is again useful when we are using what is known as tensor board. Otherwise it doesn't have much value. This additional name doesn't have much value. In this our case also, we will be seeing the graph, and that's why I'm using this. But otherwise, this having additionally a name usually doesn't add much value. All right, so let's create a constant. I created a constant. Now let us see what's going on in the graph. So I will just say operations is equal to get operations, and if you see here, now you remember here it was blank. Now you see the first operation is showing up, and this a, that's the reason I put here. So it is showing as a, and it says that, okay, you have performed an operation and there is a constant. You have created a constant. Okay. All right. So let's move on. Let's say we want to create a second constant, and this is b. So if I see what are the operations, list of operations that have been performed, you see here there are 2 of them. So you have operation a, which is a constant, then you have an operation b, another constant. You recall, in the term operation here is not very intuitive, right? So we are just creating constants or numbers or variables, and it is saying it's an operation. But that's a terminology in TensorFlow. Everything is an operation here. Okay. All right. So then what else? Let's say I want to create a third operation, and that is basically adding, this is a real operation in normal sense as well. So let's say I'm creating C, which is adding A and B, and the C value obviously will be A plus B. Okay. Now, if we want to see what is in C, and we say C, you see here, it is not showing 30. It just says it is a tensor and it is of type int32, right? Because we have not executed the graph. We are still only building the graph. I hope this makes it easy to understand. Okay, so we are just building the graph. We have till we do a session and run a particular operation, you're not actually executing anything. Okay, you're just building the graph. All right, so now let us see what are the operations. We have done A, B, and now C. So you will see there are 3 of them, A, B, and C. Okay, now let's do one more operation, which is D. And here I am doing multiplication. Remember we did a tf.add, now I'll do tf.multiply. And I'm multiplying A and B, and I'm calling this operation as D. So A has I think 10 and B has 20. So D will be actually 200 when we execute it. Right now it is just a tensor and it is of shape int32. Okay. And once again we can see what are the operations, A, B, C, D. And let's do one last operation here, which is E, which is once again multiplication of C and D. Now that C has 30, which is A plus B, and D has 200, which is A into B. So now C into D will be 30 into 200, which is equal to 6000. But as we have seen earlier, that multiplication will not happen right now. So now you have built a fairly simple but operation graph, which consists of A, B, C, D, E, 1, 2, 3, 4, 5 operations. Okay, so you built a small, it's not a very complicated one, but a simple graph. Now you need to execute these operations. So what you need to do, you need to create a session. Okay, so ses.tf is equal to session, and then you can run these session, print ses.run e. Now, am I missing something? Do I have to initialize the variables? That's a question for you. Think and tell me. Do I have to initialize the variables? Then remember, I ran one piece of code. I think you must have got the answer. I don't have to, because I'm just using all constants here. I have not used any variable here, right? So I don't have to execute that piece of code to initialize the variables. So I can just create a session and run any of the operations that I want to run. So in this case, I'm running session E, operation E, right? This operation E. Now I can actually run individually. Instead of doing directly E, I could have run only A, or I could have run B, and so on and so forth. But in this case, I have run E, which in turn will do all the required computations, which is, for example, assigning the value to A and B and C, doing the multiplication and so on. All those operations will be performed, which are required to do the computation of E. Okay. Now, there is a small piece of code that you can use to find out what are the various operations that are there in this particular graph. In this case, of course, it was very easy, very straightforward. I have created A, B, C, D, E. But in normal programming, in real life, this can sometimes help to see what is there in your graph, what kind of operations are going on in your graph. So you can write this piece of code, and it may sometimes help debugging as well. Okay. All right. So I finished my session. What do we have to do? We need to close the session, right? Because I did not use the with block. So I need to close the session as a good practice. So I close the session. Good. So that's how the graph works. I hope it was helpful in understanding how variables and constants and placeholders are created. In the previous example we saw, and how exactly you create a graph and then you actually execute that graph. That's the way TensorFlow program works. That's the structure of TensorFlow program. Okay, so now that we understood the structure of TensorFlow programming, let's take an example, and a classification example, and take some real data from outside, external data, CSV file, and try to solve a classification problem. For that, let's first go back to the slides and understand what is the problem statement, and then we will come back. Okay, so what is the case here? We have some census data, and which has all these features or variables, like the age of a person, what class, work class, what is his education, what is his marital status, gender, and so on and so forth. So there are a bunch of features that are available, and we have to basically classify, or not classify, we have to build a model for classifying whether the income of this person is above 50K or below 50K. Okay, so there is actually a label data available. We will then try to build a model and then see what is the accuracy. So that this is a typical machine learning problem actually, but as I said, TensorFlow can be used for doing machine learning as well. So we will, as a simple example, we will take machine learning. So this is how the high level the code looks, and in TensorFlow programming we also take help of regular Python libraries, like for example it could be NumPy, or it could be scikit-learn, or it could be pandas in this case. And because before you actually develop, or before you train your model, create your model, you need to prepare the data into a certain format. And sometimes if you're doing machine learning activity, you all are familiar, those familiar with machine learning will know, you need to split your data into training and test data sets. So all that can be done using regular non-TensorFlow libraries, right? So these are like regular Python libraries, pandas, scikit-learn, and so on. So we use that and then prepare the data and then use TensorFlow for performing either the machine learning or deep learning activity. Now, so what is the advantage of using TensorFlow? The main advantage is that TensorFlow offers high-level APIs, right? We talked about that. So in this case, we will be using, I'll explain what is in the slide, but before that I wanted to just show you what is the API that we will be using. So we will be using the estimator API. We will be using the estimator API to create a classifier, what is known as a linear classifier. Now, in order to do that, you need to prepare the data, and you need to prepare the data into a certain structure or format, and the API itself needs to be fed in a certain way. So that is exactly what we are doing before we get into the regular TensorFlow code. Okay, so these slides will quickly show you what exactly is happening, but I will take you into Jupyter Notebook and run that code and show you. So here we are importing the data. The data is, the name of the file is census_data.csv. It's a CSV file, and then there is income bracket is one of the columns, which basically is our target. That is what is used. That is the label rather. But this doesn't have numeric values, so it has the income. So we need to convert that into binary values, either 0 or 1. So that's what we are doing here, and then we are splitting using scikit-learn. We are doing splitting of the data into test and training, right? So this is a standard scikit-learn. People, some of you who are familiar with traditional machine learning, and you have done machine learning in Python using scikit-learn, will immediately recognize this. This is a sklearn is scikit-learn, and there is a readily available method to split the data into training and test. That's what we are doing here. And then you need to create what is known as feature columns and input functions before you can call the API, estimator API. That's what we are doing here. And there are different ways of creating the feature columns for numeric values and for categorical values, or rather for continuous values and categorical values. Okay, so that's what has been two types we are doing here. We will see again in the code as well. And then you create your model. So this is basically model is equal to tf.estimator linear classifier, and then you're feeding the feature columns, and also subsequently you will call the training by passing the input function, and you specify how many iterations to be done for the training process. And again, this is all typical machine learning process, so there is nothing specific for TensorFlow here. And then you evaluate your model, because this is classification model, so you can again take help of the scikit-learn to test the accuracy and get the reports evaluation, perform the evaluation and get the report like this one. Right, so this is the classification report, and you will see what is the precision, recall, F1 score, and so on. Again, this is a standard machine learning process. All right, so that's pretty much as far as the code here is concerned. Once again, let me take you into our lab, and we will get started with this particular code. Now, let me clear out the outputs so that you can step by step you can see the output. So this is our data, and we will actually this is just a display here. The code starts from here. So before even we start with our TensorFlow part of it, as I mentioned, we now remember in the previous examples the data was kind of cooked up. Internally we created some data and we were using it, right? The constants, variables, and so on. Here is a real life example. So you are actually getting data from outside. So before we get into TensorFlow, this is actually regular Python code. So we are using pandas, for example, to create our data frame. So we will import pandas, and then we will basically read our file into a pandas data frame, and this is how the data looks, right? And if you do ahead, it will give you about 6 readings or observations, 5 or 6 observations, and then you can take a look at how your data is looking. So for example, you have age, work class, education, and so on and so forth. Okay, and you see here this last column, income underscore bracket, it says whether the income is greater than 50k or less than 50k. So this cannot be understood, or this cannot be fed into our model, or so that's the reason we need to convert this. This will not be understood, right? So this needs to be converted, saying okay, maybe less than 50k is 0 and greater than 50k is 1. So that conversion needs to be done before we feed it into our model. So that's what we are going to do as we move forward. So this is the code for doing that. Okay, so we take this and then we define a function and then we run that function. So now we have wherever it is less than 50k, it will have 0, and greater than 50k, it will have 1. So we have now updated the data. Then the next part is to split our data into training and test data set. So how are we going to do that? We again will take the standard Python library, which is scikit-learn, sklearn library, and we use an existing function there, which is train test split. And what we are doing here is basically splitting the data into, I'm sorry, I need to run this and then this. Okay, sorry about that. So once I run this, what are we doing here? Again, those who are familiar with scikit-learn will immediately recognize I'm splitting this into test and train. I'm saying test size is 30%, so 30% of the data should go into test and training should have 70%. Okay, so that's all we are doing. 0.3 indicates 30%. So you can, again, this can be individual preferences. Some people do it like 50-50, some people 20-80, and in our case we are doing 70-30. So training is 70 and test is 30. Okay, all right. So so far we've been doing regular non-TensorFlow stuff. So preparing the data so that we can now use for TensorFlow. And in TensorFlow, what we are doing is we will be using the API called estimator. Now estimator, in order to call estimator, you need to prepare what is known as feature columns. So feature columns have to be in a certain format. Basically it is nothing but the columns. We have to put them in a certain format. And then when we are calling the training, we need to pass what is known as an input function. Again, a certain way in which you need to pass that function. So that is what we need to do before we create the model and run the model for training. So the next few lines will be doing that. Quick look at, before we even get in once again into the TensorFlow code. So this is just showing us what are the various columns, names of the columns of this data. Okay, so that is what is shown here. And this is more for when I was writing the code, I could copy paste from here. That's the reason this line of code is there instead of typing in these values. Okay, good. So now is where the actual TensorFlow action starts. So I import TensorFlow and now I will use this feature column functionality to create my feature columns. And there is a certain construct how you create the feature columns. Again, probably the details of that is out of scope here, but just that you need to know that we need to create feature columns, and the way you create feature columns for continuous values and for categorical values is slightly different, and that's the reason you have two different blocks. Okay, so for categorical values you need to use what is known as tf.featureColumn.categorical column with vocabulary list. And again, within this, again, there are two ways in which you can create for categorical values. One is a vocabulary list where you know how many types are there. So for example, gender column can have only male and female. So in such a case, if there are, let's say, a finite number of values for a given column, then you use a column with vocabulary list. Okay, so and then you say what is the name of the column and what are the possible values. So in this case, male and female. Now there will be situations where the values that this column can have, okay, first of all, it is a categorical column. That means it can have names or some non-numerical values, but the number of values is probably unknown or undefined. So for example, occupation. Now occupation can have any value. It can be self-employed, it can be a software professional, banker, a teacher, doctor. So many possibilities are there, and we don't know in the given data how many occupations have been listed, right? So that is where you use what is known as categorical column with hash bucket, and you specify the hash bucket size. So what this says is there can be a maximum of 1,000 such values. So typically if you give a safe number, safely large number, so that you don't run out of these number of occupations. So I think 1,000 is a safe number. I don't think there will be more than 1,000 occupations. in a given data. So that's the idea behind it, but that's a judgment call we need to take. What should be the size of this bucket size, right? Hash bucket size. So these are two different types for categorical values for creating the feature column. So we will execute this for all the categorical columns. Obviously you need to know the type of the columns, and that is where, if you see right at the beginning, this information was provided. What is the data type, and you see here the column name and whether it is continuous or categorical. This information is provided in the census data wherever we pick this census data from. By the way, this was picked from online from a government website and we stored locally. So on that website it is mentioned, the details of this data were mentioned, and they have mentioned whether each of these columns is categorical or continuous. So that information we have to use, and we have to create feature columns using this categorical method for the categorical type of columns. And then for numeric or continuous values, you just use what is known as feature column dot numeric column. Okay, so these are all continuous or numeric values like age, education number, capital gain, capital loss, hours per work. These are all numerical values or continuous values, right? So you just say tf dot feature underscore column dot numeric underscore column and then give the name of the column. So once you do that, I think I have executed the previous one. Yeah, this one. Now, so your feature columns are ready, and you need to basically create a vector of all these columns, and we call that as feat underscore calls, which is like a short form for feature columns. Now, as you have seen, I've mentioned earlier also, there are two things that are needed. One is the feature columns and the another is the input function. So feature columns to first create the model, and then to train the model you need to create an input function. So now we have the feature columns ready. Next is to create an input function, and there is a certain way in which you need to, this construct is pretty much a very common construct, so we will use that. So the input function takes these x and y values for training and tests. You remember these are, the x train is the x values of the training data set, and y train is the labels of the training data set. So that's what we are using here, x train, y train, and then we specify what is the batch size. Batch size, you remember I mentioned, this is what will say how many records need to be read each time, right? So typically when we are doing the training process, we don't get the entire data in one shot. We do it in batches. So what size you specify here. Number of epochs, in this case we just say none, but number of epochs is again probably the definition is not required here, but at a very high level, how many times the entire data has to be passed through the model, right? So if you have 1000 records and you pass all the 1000 records 3 times for training purpose, then you call that as 3 epochs, right? So there is a difference between the batch size and epochs. So when, let's say we have 1000 records and you're saying batch size is 100, that means there will be 10 batches, right? So if you take 10 batches, then that is 1 epoch gets completed. Okay, then the training obviously doesn't get completed in one round. Okay, so you need to pass this data again, maybe a second time or a third time till you get the right accuracy. That is known as epochs. Okay, again, if you need more details about this, you may have to go through the machine learning tutorial. I think it becomes much clearer. Okay, so you have your input function as well. Let's execute that. Okay, and now we are ready to use the API, right? So what will we do? We will create the linear classifier using tf.estimator.linear classifier, and this guy needs feature columns, right? So that's why we did all that, so much of manipulations to create this feature columns. So we have feature columns, so we pass that and we create our model. There may be a few warnings, don't worry about that, so we will just ignore that. And now we use that model, and what we did is we created an instance of the model. We have not really run anything, we just created an instance of the model. Now we will create the node for training. So model.train, and this needs the input function. Remember we created the input function, so we need to pass the input function, and then we say the steps is now telling how many iterations this training has to be run. So we are saying 5000. And this it will probably take a little long, so we will, okay, but that's fine. I think we will leave it 5,000. Sometimes if you have probably a less powerful machine, you can cut it down to maybe 1,000 or something like that. But in this case, I have a fairly powerful system, so I think it shouldn't take much long. Let's go ahead and give a couple of minutes for it to get over. Okay, so let us go back. Yeah, I think this is done. You see here the hourglass has disappeared. That means this computation is done. Yes, okay, this is done, right? Saving checkpoint for 5,000. That means it is done. So training is done. So now what we have to do? We need to do the evaluation. So again, this is a standard machine learning method. So methodology rather. So training has been done with the training data set. Now you need to evaluate using your test data set. So that's what we are doing here. For example, you see here x_test is the test data set. Remember, we used scikit-learn to split the data into training and test data set. So x_test. And a quick question, why are we not using y_test here like we did in case of training? Obviously, we are expecting the model to predict the values, y values, right? So that's why we don't pass the y values here. All right. So let's execute this for doing the evaluation. All right. And then we put them in a proper format because the output doesn't come out in a proper format. So we put it in a list format, and then we can just check. Yeah. So this is done, and we can check what is the first element in this, what is the probabilities, and so on. So it's just a quick way to see if the values are there or not. You can take any value here, right? Any element here. All right. Now that the testing is done, what we need to do, again, we will probably put them in some kind of this is more of a formatting thing. We will just run through quickly, and then we will use once again scikit-learn for finding out the accuracy and so on, because scikit-learn offers what is known as a classification report functionality. So we will use that and find out how well our model has performed. So you see here again, people with machine learning background will be immediately able to recognize this. So it gives us what is the precision, what is the recall, and F1 score. This is pretty much like you're getting like almost 85% accuracy, which is pretty okay. And there are other ways to increase the accuracy. For example, you can run the training for more iterations. That is one way, get more data and so on and so forth, or use this is a linear classifier. We could have used a non-linear classifier and so on. So again, multiple ways of doing it to increase the accuracy. But the idea here was to quickly show you a piece of TensorFlow code, and that's what we have done here.
Hey there learner, Simplilearn brings you Master's Program in Artificial Intelligence created in collaboration with IBM. To learn more about this course, you can find the course link in the description box below.
We had the original TensorFlow release of 1.0, and then they came out with the 2.0 version. And the 2.0 addressed so many things out there that the 1.0 really needed. So when we start talking about TensorFlow 1.0 versus 2.0, I guess you would need to know this for a legacy programming job if you're pulling apart somebody else's code. The first thing is that TensorFlow 2.0 supports eager execution by default. It allows you to build your models and run them instantly. And you can see here from TensorFlow 1 to TensorFlow 2, we have almost double the code to do the same thing. So if I want to do with tf.session or TensorFlow session as a session, the session run, you have your variables, your session run, you have your tables initializer, and then you do your model fit. X train, Y train, and then your validation data, your X value, Y value, and your epochs and your batch size. All that goes into the fit. And you can see here where that was all just compressed to make it run easier. You can just create a model and do a fit on it, and you only have like that last set of code on there, so it's automatic. That's what they mean by the eager. So if you see the first part and you're like, what the heck is all this session thing going on? That's TensorFlow 1.0. And then when you get into 2.0, it's just nice and clean. If you remember from the beginning, I said Keras on our list up there. And Keras is the high-level API in TensorFlow 2.0. Keras is the official high-level API of TensorFlow 2.0. It has incorporated Keras as tf.keras. Keras provides a number of model-building APIs such as sequential, functional, and subclassing, so you can choose the right level of abstraction for your project. And we'll hopefully touch base a little bit more on this, sequential being the most common form. That is, your layers are going from one side to the other. So everything's going in a sequential order. Functional is where you can split the layers. So you might have your input coming on one side, it splits into two completely different models, and then they come back together. And one of them might be doing classification, the other one might be doing just linear regression kind of stuff, or a basic reverse propagation neural network, and then those all come together into another layer, which is your neural network reverse propagation setup. Subclassing is the most complicated as you're building your own models, and you can subclass your own models into Keras. So very powerful tools here. This is all the stuff that's been coming out currently in the TensorFlow Keras setup. A third big change we're going to look at is that in TensorFlow 1.0, in order to use TF layers as variables, you would have to write TF variable block. So you'd have to predefine that. In TensorFlow 2, you just add your layers in under the sequential, and it automatically defines them as long as they're flat layers. Of course, this changes a little bit as the more complicated tensor you have coming in, but all of it's very easy to do, and that's what 2.0 does a really good job of. And here we have a little bit more on the scope of this, and you can see how TensorFlow 1 asks you to do these different layers and values. If you look at the scope and the default name, you start looking at all the different code in there to create the variable scope. That's not even necessary in Tensor 2.0. So you'd have to do one before you do what you see the code in 2.0. In 2.0, you just create your model. It's a sequential model, and then you can add all your layers in. You don't have to pre-create the variable scope. So if you ever see the variable scope, you know that came from an older version. And then we have the last two, which is our API cleanup and the autograph. In the API cleanup, TensorFlow 1, you could build models using TF-GANs, TF-app, TF-contrib, TF-flags, etc. In TensorFlow 2, a lot of APIs have been removed. And this is they just cleaned them up because people weren't using them, and they've simplified them. And that's your TF-app, your TF-flags, and your TF-logging are all gone. So those are three legacy features that are not in 2.0. And then we have our TF function and autograph feature. In the old version, TensorFlow 1.0, the Python functions were limited and could not be compiled or exported, re-imported. So you were continually having to redo your code, and you couldn't very easily just put a pointer to it and say, hey, let's reuse this. In TensorFlow 2, you can write a Python function using the TF function to mark it for the JIT compilation, for the Python JIT, so that TensorFlow runs it as a single graph. Autograph feature of TF function helps to write graph code using natural Python syntax. Now we just threw in a new word in you, graph. Graph is not a picture of a person. You'll hear graph X and some other things. Graph is what are all those lines that are connecting different objects. So if you remember from before, where we had the different layers going through sequentially, each one of those white lined arrows would be a graph X. That's where that computation is taken care of, and that's what they're talking about. And so if you had your own special code or Python way that you're sending that information forward, you can now put your own function in there instead of using whatever function they're using. In neural networks, this would be your activation function, although it could be almost anything out there depending on what you're doing.
With this, we have come to the end of this Basics of Deep Learning. If you like this video, subscribe to our YouTube channel and hit the bell icon to never miss any updates from Simplilearn. If you need any help opting for this course, please let us know in the comment section below. We will get back to you as soon as possible. Until next time, thank you, keep learning and get ahead.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.